Let's see, am I live? Gotta copy this. And okay, it should be good. Yep, the stream works. Okay, so I'm not sure how this is gonna go. I'm just gonna go ahead and try to implement this paper, LeWorldModel from ArcSiv. I have not read this in full yet. I have only taken like a small skim at what this is. And I of course know about this paper and I know like sort of what it does. The goal here is I just read this, I try to understand it. And I'm just gonna go ahead and implement it and see how this goes. So, I mean, let's just hop right into it. Joint embedding predictive architectures offer a compelling framework for learning. Yep, this is JEPA. The existing methods remain fragile, rely on complex multi-term losses, exponential moving averages, pre-trained encoders, or auxiliary supervision to avoid representation collapse. I wish they would mention the other methods explicitly here, but they do compare later in the paper. They show Dino or Dino or whatever you call it and other stuff, but I really wish they just called them out here explicitly. Pre-trained encoders or auxiliary supervision to avoid representation collapse. In this work, we introduced LeWorldModel, the first JEPA that trains stably end-to-end from raw pixels using only 2 loss terms. An X embedding prediction loss and a regular enforcing Gaussian distributed latent embeddings. Yeah, this is sort of huge. No wonder this blew up like 2 months ago, given literally this sentence here. Hold on, let me finish reading the abstract. This reduces tunable loss hyperparameters from 6 to 1 compared to only existing end-to-end alternative with 15 million parameters trainable on a single GPU in a few hours. LeWorldModel pans up to 84 times faster than foundation model-based world models while remaining competitive across diverse 2D and 3D control tasks. Beyond control, we show that the world model latent space encoding's meaningful physical structure through probing of physical quantities. Okay. Surprise evaluation confirms that the model reliably detects physically implausible events. Okay. So just to sort of, this is how I think this works right now. These 2 encoder blocks, the encoders are JEPA, and I'm not sure what the predictor is made out of. I don't know if the predictor yet is like a feed-forward neural network or if it's like a transformer. I don't know what they use for the predictor to predict the next JEPA state. I don't know if the predictor is like JEPA. I don't know what's this. So we might as well just copy this link. Let me send it to my AI here. Can you tell me the predictor in this? What architecture does it use? Does it use transformer, regular FFN, or something else? So kind of the whole point of JEPA is you give it 2 images, right? It's best to just like draw this. So this is the understanding I have right now. I don't know if this understanding will like change after I read this paper. Probably will. But you have JEPA here. This is your JEPA block, joint embedding predictive architecture. This is one block. This is another block. And during training, you give it an image. Let's call this, I don't know, O, for lack of a better term. You give JEPA an image here. And it's supposed to output a representation. This is simply a vector. And in here, you give the exact same JEPA, the same image, right? But this image is like distorted. It can be masked out. It can have any amount of like arbitrary distortions. And the whole point is that when you give it the same image and it's distorted, the representation that it outputs from that image, the vector, that's like an easy way to think about it. These 2 should be maximally similar if these images are the same, right? Use the same source image. And essentially, if these 2 images are dissimilar, say this is an image of a dog and this is an image of a cat, then the 2 vectors are trained to be maximally dissimilar. And the whole point of this is that over enough time, when you train on enough images, what ends up happening is that you get like a supposedly valid representation for any image, arbitrary image that you give it, right? Not sure. Like if you were to give it an image of a golden retriever and then you give it an image of another golden retriever, those two in latent space, which is n-dimensional, are going to be very close to each other. And if you then give it maybe like an image of a dog that will also be sort of close to the image of golden retriever, which will be closer than if you gave it an image of a wolf, which will be way further away than if you give it like an image of like a human or something, right? So the whole point is that the representations that JEPA builds in codes in the architecture, they make sense, such that when you train a predictor on it, or you do any sort of computation on representational space, it is way easier for whatever is doing that computation to actually like draw parallels or whatever. So let me check what they used here. The predictor is a transformer, not just regular FFN. Okay. Specifically, the paper says the predictor is a transformer with 6 layers, 16 attention heads, and 10% dropout. It's very funny that for, since this whole JEPA thing emerged from Jan LeCun being like, oh no, transformer could never scale. These two things actually are very interlinked, transformer and JEPA, at least how they use it in this paper. But I'm sure his argument wasn't that transformers are useless. I'm sure his argument was like transformers by themselves are not, they're not going to scale up to AGI, which, I mean, in my opinion, I don't know, honestly. They can already prove crazy like math conjectures. They can already help in training. They might scale themselves into a better architecture, but whatever, that's philosophy and we're here to implement the paper. The predictor, okay, yeah. Adaptive layer norm. There are many things in here, like I don't know what adaptive layer norm is, that I'm gonna have to learn if I'm going to want to implement this. I mean, I don't have to implement it one for one, but I suppose like a good enough implementation will do. It takes a history of latent frame embeddings from encoder and predicts the next latent embedding autoregressively using causal masking. Okay, yeah. It's just regular. This is just regular stuff for transformers. The predictor is implemented as a VITS backbone with learned positional embeddings and causal masking over the observation history. Okay. Encoder, VIT tiny image encoder. Okay. Transformer. 6 layers, 16 attention heads. Okay. Yeah. Oh, actually, didn't know. I didn't know that for JEPA, like most of everything that is being used is transformer. Well, I guess that makes sense because JEPA is in reality just a training objective. Like you're training it to build representations first and then do computation on representation space, not necessarily like a new architecture. Now that's my bad. But I guess that's why I'm implementing the paper to learn, right? Causal temporal masking, action condition via eta ln, projection head. Okay. I really don't like it when they put these images so early on, like right after the abstract. Like I don't know how I'm supposed to interpret this. Other than like super high level, but let's keep reading. This SIGREG block here is interesting to me. Figure 1, the world model training pipeline. Given frame observations O1T and actions A1T, the encoder maps frames into low-dimensional latent representations. Okay. Okay, I'm really gonna have to understand that SIGREG term here. Oh my. Yeah, this is getting freaky. Okay, I get what's going on here. Yeah, it's basically this image, and I shouldn't have bashed it. So the predictor, which is a transformer, is going to take the representation from the encoder, which is also a transformer, and an action, right? So it takes representation and any arbitrary action, and what it's supposed to be predicting is the representation at t+1. So say I have, I don't know, like in here, like this robotic arm. I suppose the action here was like, okay, down, whatever is used to arbitrarily represent the move down action, right? And it has the representation. It outputs the representation that is supposed to happen later. And you can then check with the same encoder using, MSC loss or whatever, to see what the representation, what was the difference between these two, and then train on that. And this sigreg term, stands for regularization, right? The whole point of this is that these two encoders don't just collapse to outputting just nonsense, right? They talk about, because these two encoders, they could output essentially the same thing, which minimizes MSD loss. Say, I don't know, you give it an image of a golden retriever, right? And they both output, say it outputs nonsense. Every single element in the vector, every single scalar in the vector is like a 1, which is like, that makes absolutely no sense. There's just no valid representation there. But the loss, if you were naively only taking mean squared error, then that would say, oh, everything's perfect here, we're done, even though the representation has like absolutely no value inside of it. And that's why you do sigreg. Interesting. Let's keep reading. PLDM 6 hyperparams under. Oh, and right here they actually start comparing. Oh, here's Dino. Okay. 6 hyperparams under specified anti-collapse reg. LeWorldModel 1 hyperparameter provable anti-collapse. Under specified anti-regulars. I don't know. The only example here I'm familiar with is actually LeWorldModel. I don't know PLDM or Dreamer or TDMPC. 6 hyperparams under specified anti-collapse reg. 1 hyperparam provable anti-collapse. It's interesting. I wonder what they mean by provable anti-collapse. This is what I'm talking about, with that these two encoders can just collapse to outputting nonsense representations, kind of like cheating the mean squared error loss. It's crazy to me that they use the word provable here. Like, what do you mean you proved the encoders here can't reliably cheat the mean squared error loss? That's going to be very interesting here. LeWorldModel end-to-end learning. Yep, this is huge too. That you can train the representation and the predictor jointly. Because training the predictor separately, I mean, if you want to scale these things, which is, I mean, the whole point of like JEPA right now is in a state where it's very small and it's not proven to scale. You can't do frozen training, or at least it's like very iffy to just have frozen blocks in your training when you're supposed to be scaling in like an architecture or philosophy here. So it's interesting that this is end-to-end learned, and then that also explains why this paper was so huge. LeWorldModel, task agnostic, reconstruction free. This is very needed as well. If you want to make a general architecture, I don't really believe in architectures that are task specific. I mean, the whole point, while that when it comes to like why did AI blow up and why is it so good now and why can it just learn, is because it's generalizable. Pixels based, reward free. Okay, awesome. Characteristics of latent world model approaches. Methods are grouped by training paradigm. End-to-end methods. PLDM learn both the encoder and predictor jointly from pixels without relying on pre-trained representations or heuristics such as stop gradient. Okay. Okay, so it appears PLDM is similar to LeWorldModel, but instead of doing the computations and predictions in representation space, it does them in pixel space, which is, at least off of what I know, very unstable for visual tasks, but for language modeling tasks, doing them in the space of the input did actually succeed, right? Whatever your definition of success is with transformers and GPT models and all that. Like there's this argument that the reason they succeeded is because the space, the possible output space for language tasks is way lower. What does like an embedding layer like output, right? Maybe like 128K different tokens. I don't know how many tokens. Say something like, we should actually look it up. Tokenizer, GPT 5.5 tokenizer, total tokens. Just to make sure that I'm like outputting total vocabulary. There we go. It's called vocabulary. The space of possible outputs here for like transformers typically tends to be in the hundreds of thousands range. If you're doing a vision model and you have to output the following frame and you have to output pixels, then the actual output space here, it's several orders of magnitude higher, because imagine how many pixels are in an image, all the colors that the pixels can be. And the issue with the difference here between pixels and tokens is that any specific pixel doesn't really matter much. Like I could have an image of a dog, and if I color the pixel at position 437, 512 completely black, that's not going to change much. But if I change a word to something completely different and say, I don't know, a couple of paragraphs, then it's just, for that specific sentence, it's not going to make sense at all. So I see why it would make sense to kind of bash other architectures here, or why there would be such a push for, when it comes to vision tasks, do them in representation space instead of pixel space. Okay, and now we finally get to the introduction. Oh my god. I am really intrigued to understand more about these anti-collapse guarantees. Because as far as I know, like the main problems with JEPA and representational learning was that you couldn't necessarily avoid, or it was like a task. It was like an actual problem to avoid representational collapse. So let's see. Introduction. Essential goal of artificial intelligence to develop agents. Yes. So core skills. Using a single unified learning paradigm. The represents direct from sensory puts surroundings while hand engineers say representation of domain specific calibration. This is kind of this is calling out a lot of techniques here. Hand engineers stage representations or domain specific calibration. It's almost calling out all of reinforcement learning, actually. Like the people that handcraft like tasks, say does the code work, or did you prove the math theorem, or etc. Many of the things that these big labs are doing, like Anthropic, OpenAI, is literally handcrafting environments such that they can use reinforcement learning. And they handcraft tune their words, and it's all just gone like haywire. Like they even have like the agents come up with rewards, and there are papers saying that agents can come up with better rewards than humans can for these specific RL environments. So I guess this is kind of like a jab at all that philosophy, and I guess why that would make sense. If you have to train it on thousands of hand-tuned environments, then what's the elegance in that? And is there a better, much simpler, to quote the paper, unified learning paradigm that can scale up to general intelligence? Interesting. Vision is ideally suited for this aim. Yep. Cameras are inexpensive and scalable, and learning for pixels enables fully end-to-end training from raw sensory. Wait, hold on. I think I skipped something. Directly from sensory inputs. Yep. Vision is ideally suited for this aim. Cameras are inexpensive and scalable, and learning from pixels enables fully end-to-end training from raw sensory input to action. This is also desirable. World models are a powerful family of methods that learn to predict the consequence of actions in the environment. When successful, world models allows agents to plan and improve, and to improve themselves solely from their model of the world, i.e. an imagination space. They call it imagination space. I would call it just representation space, but I don't know if I'm missing something. This is particularly valuable in the offline setting, where agents must learn from fixed data sets without environment interaction, leveraging the model to generate synthetic experience and evaluate counterfactual action sequences. This is all very interesting, because we are running out of offline data. Like frontier models right now, they're trained on I think the upper end right now is at 100 trillion tokens, and then they go to online reinforcement learning, where they are put in an environment, and who knows how many tokens are used for that. Probably more than 100 trillion, because 100 trillion is for the pre-training. And labs are saying, if you look at like what XAI posts with Grok, they say that they spent most of the computation on the reinforcement learning side now. So I mean, you can easily say that these things are being trained on a quadrillion tokens, 10% of those being offline and 90% of those being online RL. If you plan and improve themselves solely from their model, there's a typo here, of the world, i.e. imagination space, is particularly valuable in offline settings. If you can somehow increase the signal that is being obtained from offline setting, that would be massive. There's this whole debate going on where how many trillions of tokens does a 3-year-old consume versus a GPT, and you realize that GPT is consuming orders of magnitudes more than that. Like GPT, if you just look at textual tokens, like just text, GPT for training and like all those models consume way more than several human lifetimes in their training. But that is only if you look at text tokens. If you look at vision tokens, then I think the 3-year-old then has consumed more tokens. But then again, that is misleading, because the humans, they don't do computation in pixel space, right? First of all, these two things aren't really like comparable in the first place, but assume they are somehow comparable. Humans wouldn't even do a computation in pixel space. You can see why like this whole argument of we need to move to representation space or imagination space, as this paper calls it, would make more sense. Leveraging the model to generate synthetic experience and evaluate counterfactual action sequences. A recent popular approach for learning world models is joint embedding predictive architecture. There's something I need to open another browser. Hold on. Does this work? No, it opens it here. What a pain. What a pain. Because I want to be able to have this stream, but in my browser here, I haven't coded it such that it can open other windows. Let me just ask it, can you open another Zen browser window? Another purple. And let me check how that goes. Jesus Christ, I have to use AI for everything nowadays. I'm lost. To generate synthetic experience. A recent popular approach for learning world models is the joint embedding predictive arc. Yep, JEPA. Instead of, it's still, they say the word architecture, but it's more just an objective. But fine. Oh, there we go. I got the other window I needed. And now I can look at my stream while I look at the paper. I should actually add to my to-do to fix this thing in my browser here. Hold on. Okay, there we go. Hold on. Okay, this is sweet. Okay, awesome. I go here, I do this. Instead of attempting to model every aspect of the environment, JEPA focuses on capturing the most relevant features needed to predict future states. Concretely, JEPA learns to encode observations for learning world models is a joint embedding predictive architecture. Instead of attempting to model every aspect of the environment, JEPA focuses on capturing the most relevant features needed to predict future states. Yep, this is, you get relevant features in the representation. Concretely, JEPA learns to encode observations into compact low-dimensional latent space and models temporal dynamics by predicting the latent representation of future observations. To a compact low-dimensional latency. Yep. This works how I thought it did. Models temporal dynamics by predicting the latent representation of future observations. Wait, hold on. JEPA learns to encode observations into a compact low-dimensional latent space and models temporal dynamics by predicting the latent representation of future observations. I did not know about this. What do you mean it models temporal dynamics? I thought that JEPA was only immediate representations of input. LeWorldModel. I thought LeWorldModel was the one that introduces temporal dynamics, and then from temporal dynamics, what you can do is use the search algorithm that they use through representation space to find and get to a goal. Might as well just ask my boy here. What do they mean by this? Oh, not that. That's the stream. Can I copy this, please? Nope, I cannot. I'm just gonna have to type it out. What do you mean by... Move this here. And model. Modeling temporal dynamics by predicting the latent representation of future observations. I thought that was introduced by LeWorldModel and not necessarily by JEPA. And I thought that this paper was the one that actually introduced temporal dynamics. You can find more about this in the introduction section. Let's see how that goes here. However, despite their conceptual simplicity, existing JEPA methods are highly prone to collapse. In this failure mode, the model maps all inputs to nearly identical representation to trivially satisfy the temporal prediction objective, leading to unusable representations. Yep, that is what I was talking about. But maps all inputs to nearly identical representations to trivially satisfy. I see. So you don't really train for things to be maximally similar and maximally different. You only train them to be maximally similar. And then you let the regularization term be the one that actually imposes that. Interesting. I thought that, negative and positive chaining here was what was being used, but apparently that's not it. Apparently it's only positive and then regularization across the positive. Learn transition model in latent space. Okay, let's see this. Transition model in latent space. Gosh, I need to turn on my AC. This is a key equation here. Oh. I'm just being stupid. For learning world models, not JEPA by itself. And that's what brings in the temporal dynamics here. Okay. However, despite their conceptual simplicity, existing JEPA methods are highly prone to collapse. Yeah. But isn't forcing a Gaussian distribution across the batch, the training batch, the same as a heuristic regularization? How does that different? How is that different from? I guess we'll see. From raw pixels without heuristic principled. Can be trained on a single GPU. Yeah, I actually did some research beforehand on this paper. They trained it on I think it was an NVIDIA L40, which is pitiful. Like when you compare it to other research teams that have like entire data centers to prove that their I don't know, like 14 billion transformer model is slightly better in GSM-8K. In here, I think they trained it using only an NVIDIA L40, which is really good for me because the flops in an NVIDIA L40 are only 3x more than the flops in my GPU here. So that should roughly mean that if I get a good utilization of the GPU, I can train this in 3 times the amount of time they trained it here, or roughly about a day. Because I think they took a couple of hours to train their model, I think that then for me I should take about a day to train something similar. Then again, I don't need it to be as good as the paper. I don't need it to achieve the same results. I just need it to be good enough, or like a proof of concept, for me to be happy here. Well, not proof of concept, like I train it and then I can see like loss going down, and I can verifiably, when I pass it through the decoder, I can see that it can do tasks that I'm not going to spoil them. It can do the tasks that the world model can do. Maybe not to the same reliability, but good enough. So this is good. We evaluate the world model across a diverse set of manipulation, navigation, and locomotion tasks, both 2D and 3D environments. In addition, we probe its intuitive physical understanding through targeted probing and surprise quantification and evaluation in latent space. Okay, hold on. Gosh. I don't know what targeted probing techniques are there. I have no idea how these people use targeted probing, so it's going to be very interesting to see how that was done here to inspect the representations. So key findings. We proposed an end-to-end JEPA method for learning a latent, world model from raw pixels on a single GPU. The method relies on a simple and stable two-term objective that remains robust across architectures and hyperparameter choices. Okay. While enabling efficient logarithmic time hyperparameter search. What? Logarithmic time. What do you mean? I thought, okay, I'll just keep reading and figure it out. Okay, I'm back. Logarithmic time hyperparameter search. I don't know what they mean by hyperparameter search. And more impressive to me is, how do you get something that's logarithmic time in anything that's going on in here? I thought the best you could do is linear, but we're about to find out. Full planning. What the? The world model. Dino. This is crazy. Push C. Fixed loops. OGB cube. This task is the one I want to train it for. Push T is essentially a task. I spoiled myself a little bit. You have a T block here, right? And you have realistic physics. Here's your T block. And then you have a desired position here. Say like this. And the model, it gets like an, I don't know if like an actuator, it gets like a circle here that it gets to control and move omnidirectionally, right? And it uses this circle to push the blue T, which, you know, has real physics, to the position dated in here, in the orange T. And the reason why this is a benchmark in the first place is because, you know, moving a T here is like awkward. To get it to this position, you have to push it here, then push it maybe on the side, and then push it from below once it's in like the correct position, right? And that's the whole point with push T. So it does 90 fixed loops, fixed flops, success rate. Oh wow. You fix the flops of both, and the success rate in push T is 90 versus 13% with Dino. I mean, they only compare with Dino, but maybe Dino's the most. I'm hoping they're good, and Dino's is like the other method that does the best, and they're not comparing it to one that does worse. But OGB cube, I don't know about OGB cube. I think OGB cube is this one, the one that's being shown here. Hold on. We can find out very easily. Left push T. Yep. Center 1. OG bench cube. This one is OGB cube. This is the one that gets the robotic arm, and it has to place the cube somewhere else. I need to know exactly what would happen. Interesting. Visually richer 3D manipulation environment. I don't know how it can accurately learn 3D like representations if it's only being trained on OGB cube for it. I imagine you would have to like, I don't know, like pre-train it on more stuff for it to accurately learn 3D representations, but I don't know. We'll see. Manipulation environment where a robotic arm interacts with a cube to reach a target position. This is 2 room. This one, center right, where an agent moves between 2 rooms to reach target positions. Yeah, and it has like a dot, and it just has to go to the dot here. Okay, this is very simple stuff. 2 joint arm needs to reach a target configuration in 2D plane. All environments have a continuous action space. Okay, great. Great. Okay, so now we know what they're talking about here. An OGB cube, fixed flops. It's interesting that fixed flops for OGB cube, you know, Dino does way better. Like in here, LeWorldModel is pretty much 8 times better or 7 times better than 7 times better than Dino and Push T. But in OGB cube, it's not even 2x, it's like 1.5x better. Which begs the question, okay, what about the architecture in LeWorldModel makes it such that in Push T for fixed flops, it's way, like, vastly better than Dino? I'm not sure. You could argue that in Push T, since you have to do all this planning and moving the T in this environment is really awkward. Maybe for planning, then LeWorldModel would be way better than Dino. And in these like tricky environments. But in an environment like OGB Cube, where the main thing you're doing is the 3D representations, I mean, you don't really need to plan how to move a T. You only really need to plan where does the robotic arm go, and how do I kind of represent the 3D scene. Makes sense why Dino does so much better than it does in Push T. Because Dino, if I'm not misremembering, is already pre-trained and it already has all those 3D priors. Meanwhile, the LeWorldModel would have to learn it from scratch off of these tasks. And even still, even with all those 3D priors in Dino, then it makes it all the more impressive that the LeWorldModel still beats it in OGB Cube, even though it's not a planification heavy task. That's interesting. Planning time and performance under fixed compute left. Planning time comparison average over 50 runs. Oh, this is average over 50. Okay. Including observations with 200x fewer tokens than Dino LeWorldModel allows the LeWorldModel to achieve planning speeds comparable to. Encoding observations with 200 times fewer tokens than Dino. Holy. Allows the LeWorldModel to achieve. Well, yeah, I guess this is why you see this crazy drop in full planning. So your planning speeds comparable to PLDM, while being up to 50 times faster than Dino LeWorldModel. Center right planning. I wonder though, like, if you weren't to do fixed flops here, and you were to just do like asymptotically, and you were to like make a graph of LeWorldModel versus Dino world model at different flops, is there a point where Dino overtakes the world model? Or is the world model asymptotically always like, or almost always strictly better than Dino? I should actually write that down and check later. Let me make maybe research and make their LeWorldModel, and I'll make a quick questions.md. And this is questions to resolve, I don't know, when implementing this paper. Is the world model asymptotically better than Dino world model? I'm not going to train Dino. I am going to train my own the world model. Dino, I'll just grab it off Hugging Face and see how that goes. That is something I really want to know. And the world model achieves strong performance across diverse 2D and 3D tasks with a compact 15 million parameter model. Jesus, that's really small in today's standards. Surpassing existing end-to-end JEPA-based approach while remaining competitive with foundation model-based world models at substantially lower cost, enabling planning up to 40x times faster. Oh my god. Competitive with foundation model. I am still interested in like, okay, what if you scale an architecture like this up to foundation level? But I guess that's not something I can really figure out just right now. We evaluate physical understanding in the latent space through probing of physical quantities. Yeah, I've mentioned this several times. And a violation of expectation test for detecting non-physical trajectories. Oh, wow. This is going to be really interesting. So they're able to measure somehow the surprise or the... essentially the surprise inside of the, I don't know if encoder or predictor. Let me just ask here, when they mention violation of expectation test for detecting unphysical trajectories, where are they measuring the surprise? Do they measure it in the encoder or predictor block? Or both? That's going to be really interesting. But I imagine this is not exclusive to the world model. I imagine you can still do probing on Dino or do probing on other types of world models that people have been trying to do in the research and still find like surprise features right inside of them. That said, let me check here. The measure suppresses prediction error in latent space. Oh wow, I see. So it's not. So it's not a probe. You're not really measuring like representations or features inside of the model. You're just measuring the prediction error. Yeah, I guess that would make sense. I was way overcomplicating myself. So it is not surprise inside the encoder block. Yeah, it is surprise. It's the mismatch between the encoding of at t+1 and the encoding at t equals 0, right? Which it would make sense why that happens. The predictor's expected future latent space and the encoded latent representative of the actually observed future frame. As an internal activation metric, it is computed between mismatch and the encoded's latent representation of the actually observed future frame. Yeah. And here is basically what I was talking about. Maybe it'll be useful for me to start referring to the to this in terms of OT +1 and ZT, Z being the representation and O being the observation, right, in the world. Interesting. So both components are involved. Great. And for something that is able to predict stuff this quickly, and it is able to just kind of observe at all the possibilities, then you could do stuff in representation space. You could get pretty freaky with stuff like Monte Carlo tree search. which is something that people have tried to apply to transformers, like just sole transformers, generative pre-trained transformers, with limited success. I think Google DeepMind was really trying to do Monte Carlo and MCTS on their transformers. Well, actually, I have to fix the stream title here. I just realized. Silly me. Let me go to the panel here. If I can even figure out how to do this. Let me go here, Vim browser camera framing options. Okay, great. Can you open in Vim browser the stream studio so that I can change the title of the stream while I'm streaming? I'm streaming right now and just noticed that title was inaccurate. Yeah, the title of the stream is Final GPU FFmpeg 1080p 60 validation. Because I was really struggling with getting like a script that I could stream with very easily. Like I just hop on my terminal and I just do like, YouTube that stream, and that immediately starts streaming my entire screen, and I was really struggling there. So let's see. Can you change the title to streaming until I build AGI day 1, implementing LeWorldModel? Let's see if he can do it for me. Half of me is scared of clicking anything in this dashboard and having it leak API tokens, like access tokens or something. Well, he's doing it. I wonder if it changes now. He updated it. Okay, perfect. Okay, the stream title is correct now. Okay, back to what I was doing here. Predictor transformer. Okay, here. So, world models aim to learn predictive models of environment dynamics from data. Where were we? Oh, we were here, in violation of expectation. World models aim to learn predictive models of environment dynamics from data, enabling agents to reason about future states in imagination. I really dislike that they call it imagination. Just call it representation space, because that's what it is. Or I guess imagination representation space, because you are looking at several different possible representations that could happen, so you could kind of equate that to imagining. I just don't. I'm not a big fan of research papers anthropomizing, or however you say that word, anthropomizing or anthropocizing these models or their techniques. I think it is very romantical to go ahead and say like these architectures or these models, they work in a similar way to how the human brain works. And it is like very attractive to say things like that, but I would disagree that is the right naming scheme here. Either way, I'm just being pedantic. Let's just keep going. A prominent class of world models consists of generative approaches that explicitly, oh my god. Class of world models consists of generative approaches that explicitly model environment dynamics in pixel space. And this is extremely expensive if you're doing pixel space. If you have to produce an HD image, just how much, like a 1080 times 1920, that's already a ton of things that you have to produce. And pixel space is, it has this, it just loses itself. If you have pixel space and you have your predictor keep predicting pixel space indefinitely into the future, you get a ton of blurring. What do I mean by this? If you have, let's say a ball here, right? Let me just draw this, and you have an action go down, and you have another ball here, and these two are going to collide, right? If you're doing representations in pixel space, what usually ends up happening is that instead of picking a single outcome, what ends up happening is that the average of all outcomes in pixel space is what ends up being predicted, because how are you going to craft a loss that forces it to just pick one sort of possible future, right? So imagine you're training a pixel space predictor, right? Or like a video predictor, right? You give it frame 1 of a video, and then you tell it to predict frame 2. And then you grab that frame 2 prediction, and then you tell it to predict frame 3 from that, and so on and so forth. Eventually, there will be a frame where there's like a fork in the road, right? Where, you know, things may bounce differently or things may act differently. And when you pass that through a loss, something like mean squared error, an input maps to several outputs, because you can have a ball bounce many unpredictable ways off of just pixel space, if that makes any sense. And you end up getting a massive blur of pixels because all that could happen, or all that is likely to happen, what is outputted is the average of that. And transformers don't really have this because they don't even use MSE loss. They use cross entropy loss, because it is since the space is small enough, 200,000 vocabulary, you can just pick the most likely token. You can't pick the most likely like frame out of like many possible frames, because you just can't train that. It's too much. It explodes, and you would need to have like a GPU the size of the planet to be able to do that. And that's why there's this big push to representation space. At least that's how I understand it, right? These action condition generative models act as learned simulators by producing future observations conditioned on past states and actions. Act as learned simulators by producing future observations conditioned on past states and actions. Okay. Yep. Generative world models have been usually successfully applied to simulate existing game-like environments. I have seen some of these papers. Not these, but I have seen them. Class of model consists of... Just reminds me of the very popular Descartes kind of like lucid dream Minecraft thing, where you would move and you would really interact with an AI model, and it would produce like the next frame of the Minecraft game, where it would take like an action and a previous frame. I wonder if Dreamer v4 was the one behind Descartes AI, but I'm not sure. Counter-Strike and Craft are improving policy, sample efficiency, and reinforcement learning. Other methods generate entirely new interactive simulators, e.g. Genie. Genie, this one's from Google. I have seen this one. Well, learn simulators, but these are massive, right? These they train essentially foundation models, and in doing so, you just need a massive like data center GPU farm in order to be able to train these, right? And it's just not desirable, at least to me, and at least to like the philosophy that I'm trying to grasp here. While learned simulators have also been applied to robot policy evaluation, importantly, many generative world models assume access to datasets containing reward signals. Okay, so essentially handcrafted reward signals, which is not the point, enabling joint modeling of dynamics and value relevant information for downstream reinforcement learning. Yeah. In contrast, we focus on the reward free setting, because if you don't have to handcraft rewards, then you can just keep scaling this, right? Corresponding to the setup considered in the JAPA line of work, which aims at learning generic task agnostic world models from observational data without relying on reward supervision. Okay. And they're kind of differentiating themselves, their philosophy, their JEPA philosophy from the philosophy of massive pre-trained models here. And in my personal opinion, I agree with the JEPA philosophy more because I think it's more elegant. I think I can train it. I will never be able to train a pre-trained world model, at least not with the current setup that I have. Or even if I were to spin up a cloud VM, like what am I gonna do? Am I gonna spin like an 8x H200 box? This is not gonna happen. Ideally, I want something that I can research with and train on a GPU that I can easily access. And I guess JEPA is the answer to that. And besides, I also think the idea of doing computation in representation space, what these people call imagination, is much more elegant than doing it in pixel space. And I think in the future, it will scale better. Of course, this is just a bet, right? You don't actually know until you do it if JEPA-based approaches will actually surpass transformer-based approaches in many of the things that happen here. So let's keep reading. JEPA is a framework for learning world models that predict the dynamic evolution of a system in a compact, low-dimensional latent space. This is what I call representation. Since their introduction by LeCun, JEPA methods have evolved considerably, differing mainly in their target task and in the strategies used to learn non-collapsing representations. Precisely the regularization terms that these people need, or that JEPA needs, such that you can get accurate representations, right? One prominent line of work applies JEPA to self-supervised representation learning by predicting the latent embeddings of masked input patches. Okay. I think this is the training objective where you give it two images, and one of them is, masked. And you have the source image and mask image be maximally similar, and ideally, with good regularization, these would produce a latent space that makes sense for all possible inputs. Examples include iJEPA for images, VJEPA. I know about VJEPA. I think I've heard of iJEPA, but I haven't dived into that one. For videos, and EchoJEPA and Brain JEPA. Okay, for medical data. These approaches, it's interesting. I would like to review these papers, the ones that are trying to use JEPA for medical data, because I wonder how reliable a JEPA-based approach would be for medical data where you need maximal accuracy. Like how you extract an image out of a JEPA is you use the decoder block to reconstruct the image from the representation, but if you don't reconstruct, as far as I know, images like pixel perfectly, because a representation is simply just a compression of the real world. And if you're trying to reproduce the real world from a compression of it, then what is the validity of that for settings where I imagine you need maximal accuracy? Like, I don't know if you were predicting MRI scans or if you were predicting, brain images, right? So it will be very interesting to dive into that as well for medical data. These approaches typically employ an exponential moving average of the target encoder together with stop gradient updates to stabilize training and prevent representation collapse. Okay. I want to dive into this more. When the paper talks about exponential moving averages and stop gradient updates to stabilize training and prevent representation collapse of other approaches like VJEPA and EchoJEPA and etc., what do they mean by that? Like, how does this actually work in training of those other approaches? If you could do a literature search and look at those papers as well that this paper references and tell me exactly how those papers do stabilization as opposed to how LeWorldModel does stabilization through its SIG regularization, tell me about that, and tell me about that simply. Because if you don't tell a GPT model to explain it to you simply, it will just go on and on and on. And we're already pretty deep with this paper here. However, the theoretical understanding of EMA and SG remains limited. Because many of the approaches that came prior, they focused mainly on practically getting regularization. Meanwhile, this paper is stating it proved regularization, right? Which is interesting. as they do not, in general, correspond to the minimization of well-defined objective. Yeah. A second line of work uses the JEPA recipe for action-conditioned latent world modeling. Some approaches rely on pre-trained encoders to obtain representations, which is Dino, I think. This avoids collapse but limits the expressivity of representation. Yep. Yep. That is a fair critique. Encoder, predictor, cost, and solver. I'd like to understand this graph here. The world model latent planning, given an initial observation O1 and a goal OG. Funny notation, OG. The world model learned in Fig 2 performs planning in the world model latent space. This is what they call imagination. The initial state embedding Z1 and the goal embedding ZG are obtained from the encoder. The predictor then rolls out future latent states up to a horizon H. Okay. So you basically grab it and tell it, okay, I want you to get to this OG. You have this many steps. You have steps up to this horizon H, and you let it just plan. And then you can... What do you mean update actions using a cost and a solver? I don't get this part. A latent cost between the final predicted state and the goal embedding guides a solver to optimize the action sequence. Is this like what the difference between the final decoded state and the state at the horizon? And do they always roll out the state until horizon? Wouldn't it make sense for once it it achieves a right, let's say, sequence of thought, like a right imagination, it stops itself and it says, okay, I'm done. Instead of having to roll it out to ZH every time. Because you can imagine that I'm planning a move T task or planning like task A and task B. The mental tax on that is not uniform across every single task, right? But whatever, we'll see more of that when we keep looking at the paper. A latent cost between the final predicted state and the goal embedding guides the solver to optimize the action sequence. The prediction optimization loop is repeated until convergence to a good plan candidate. Okay. So if I'm understanding this correctly, say you have your T here that you want to move in the environment. You have your target position for the T here, right? This would be in the push T task. And let me save this. And then you have the actuator here that the model can actually move. What it does is it plans trajectories or in imagination space. Like it plans, say, moving the T here, this planning, this other direction, this other direction, this other direction. And then it picks, say, the most promising one that matches the best with this once it's decoded. If I'm understanding this correctly, which I'm not sure if I am. Hopefully I am, but I don't know. We'll keep reading and see. What am I doing? I can just copy this and ask it to explain it. Let me fork it here. Can you explain this part in the paper? I'm a bit confused by the cost and solver part of the diagram. I'm not sure what they mean by that. I'm imagining that what it does is it plans several future trajectories in imagination space, and then it picks the K most promising ones. But I'm not sure if my understanding is correct here. And then we can go back here. Let me check quickly what it responded here. I don't have LaTeX in a terminal. It's trying to do LaTeX. This is gonna kill me. They're talking about common teacher-student trick used in many JEPA. What is BYOL? Bring your own learned representation, like bring your own learned model. Style self-supervised methods. The simple version. Instead of letting both gradients, this is talking about. Hold on. This is talking about what the other JEPA-based approaches used. So they used EMA and stop gradient, right, to prevent representational collapse. Instead of letting both sides of the prediction loss update freely, older JEPAs keep the target side fixed, slow moving using stop gradient and EMA. Instead of letting both sides of the prediction loss update freely. Okay. Older JEPAs keep the target side fixed / slow moving. Oh, okay, that makes sense, but that seems like a hack. Okay, so when you have your two encoder JEPAs, then what other older methods did is that the first one, the one that was encoding O1 or OT, right, would then be slow moving, and then the next one would be fast move. No, my bad. The other way around. So the one that would encode OT would be fast moving, and the one that would encode OT+1 would be slow moving. And the hope is that since these two can't update equally, they wouldn't be able to cheat. But I think that A slows down training, B doesn't fully prevent cheating by the encoders, and it can still lead to representational collapse, which is what the critique here says. Where is it? The theoretical understanding of EMA and SG remains limited, right? Because the hope is that this that stop gradient and EMA in practice does that, but in theory it doesn't necessarily prevent representational collapse. It just, by slowing one of the encoders down, you hope that they don't they produce accurate representations, which is very funny, because to me that seems really dumb as a solution, instead of just using a regularization term. I see. Then again, I haven't trained a JEPA before, so we're gonna find out. We're gonna find out how many of these opinions hold, right? Method. Okay, hold on. And let me check. Actually, is this done? Yes, it is done. Okay, so let's see what they mean by this graph here, which is what I didn't understand. Given where I am and what goal image I want to reach, encode both into latent space, okay? Then try many possible future action sequences inside the learned world model. For each one, predict where I would end up in latent space. Score each plan by how close its final predicted latent state is to the goal latent state. How would you do that? MSC? Whatever. Use CEM to keep improving the action sequence. What's CEM? Later the paper will explain. I don't need to find out just right now. To then execute the best plan, usually with replanning. Okay. So I think it's sort of what I said regarding the push T example, but it appears to be a bit more involved. Okay, we'll find out what they mean by that. To the pre-trained encoder used, where were we? But limits the expressivity of representation to the pre-trained encoder used. Yeah, these are models like Dino, that had a frozen pre-trained model, right? In contrast, PLDM learns representations end-to-end using VicReg. Oh, interesting. Okay, so we do get regularization here with additional regularization terms, at the cost of known training instabilities and scalability limitations. So the regularization terms that these newer methods like PLDM were using weren't exactly great, and that is the critique here. Okay. Several works further improve stability by incorporating auxiliary signals or architectural components such as proprioceptive inputs or action decoders. Interesting. In this work, we propose a stable method for training end-to-end JEPAs directly from raw pixels using a simple two-term loss. A predictive objective. They've said this single sentence like 3 times already. A predictive objective on future embeddings and a regularization objective that enforces Gaussian distributed embeddings. Okay. It's interesting they chose that the representations or embeddings, their theory is, okay, to prevent representational collapse, we can enforce a Gaussian distribution loss across the embedding space in the batch. Why Gaussian? Like, why specifically did you pick a Gaussian distribution? Is the question. Planning with latent dynamics. World models pioneered learning policies directly from complex latent representation of high-dimensional observations. Pioneered learning policies directly from complex. Okay. Some works leverage learned latent dynamic models to train policies using reinforcement learning. In these approaches, the generative world model acts as a simulator in which trajectories are rolled out in imagination, allowing policy optimization to occur largely in imagination and latent space. Once training is complete, the policy is executed directly, and the world model is no longer required at test time. What? Hold on. Okay, yeah, they're discussing other techniques. World models pioneered learning policies directly from compact latent representations. High-dimensional observations. Okay, I think I get what's going on here. High-dimensional observations, they just mean the input, the observation, the image, right, which is high-dimensional. They compact it into a latent representation, which that's what JEPA does. But it's not necessarily the architecture we see in the world model. And latent dynamics models to train policies using reinforcement learning. So it's sort of similar to what's going on in the world model, but they leveraging learned latent dynamic models to train policies using reinforcement learning. And these models are not needed at test time, right, at inference. In these approaches, the generative world model acts as a simulator in which, okay, yeah, I get what's going on here. So you train an actor in a fake world, an imagination space of these world models, allowing policy optimization to occur largely in imagination and latent space. Once training is complete, the policy is executed directly in the world. Okay, yeah, makes sense. That's sort of if I could like lucid dream, and I were to train tennis in the middle of my lucid dream, and then once I'm done lucid dreaming and training like tennis, I go to the real world and do the real thing. And the hope is that my learning from imagination space transfers over to the real world, which also kind of seems dumb to me. Like, I don't know. It just doesn't fully make sense to me why you would want to do it that way. Like, it seems there's one too many steps in that loop. More recent works instead perform planning directly in the latent space at test time using model predictive control, MPC. I'm brain rotted from all the MCP servers that Anthropic and OpenAI keep pushing. In contrast to imagination-based policy learning, these methods use the world model online to predict the outcomes of candidate action sequences and iteratively optimize them during execution. The model therefore remains part of the control loop at runtime, enabling adaptive decision making but increasing computational requirements. This is more similar to what the LeWorldModel is proposing. This paragraph here. Method LeWorldModel. In this section, we introduced LeWorldModel. We first described the streamlined training architecture procedure used to learn the latent world model from offline data. Okay. Yeah, because offline data is like the simulations that they do. Kind of how like they grabbed the robot dog from Boston Dynamics, and then they trained it offline. Or was it actually online RL? No. That's work I'm referencing was actually online because they did the physics engine. Like they implemented a physics engine. Okay, interesting. Here, hold on. All right, interesting. So you grab, hold on. Wow, I actually don't fully get this paragraph, what's going on here. In this section, we introduced the LeWorldModel. We first described the streamlined training procedure used to learn the latent world model from offline data. Right, so this is the representation that the JEPAs, that happens in JEPA, right? That happens in the encoder block. So you can learn a world model from offline data. Interesting. I imagine it's using the loss terms that I described above. I guess the surprise or the MSC loss in the predicted representation and what actually happened in the real world, including the data set, model architecture and training objective. Interesting. We then explain how the learned model can be leveraged for decision making through latent planning using model predictive control. Okay, I get what's going on. You use offline data to train a world model essentially under the JEPA architecture here, with the predictor and encoder blocks, which are both transformers. Then, what you can do is do a bunch of possible trajectories and optimize these trajectories such that they can achieve a goal. Right, which is what I was talking about earlier with the push T example, where you can have it imagine a bunch of trajectories in imagination space, pick the k most promising ones. Then you know once you do the rollout up to the horizon, and then once you do that, you can see the ones that get closer to the goal, and then go from those, which is very brute forcey. Like it's brute forcey that it doesn't already come up with like possible trajectories that it wants, or that it thinks like, okay, like when I'm in a push T task, I don't need to like explore everything. I sort of only explore the paths that I think are promising, and the paths that I roll out into the future and are promising, and I kind of how AlphaGo works. Right? Or kind of how like a chess engine works. You don't randomly do moves and then pick the most promising ones and then do more random variations on that. You kind of already know the good moves. You roll those out. You analyze in the future, whether you're doing Monte Carlo tree search or you're doing whatever on the rollouts. And then you pick the winning sequence. So that is like the missing piece here that I see in this paper. Then again, what if it includes something like that, and I'm just I'm kind of expecting less of model predictive control, because I haven't heard of model predictive control yet. Like I don't actually know what that is. So let me stop LARPing and just take a picture of this. Can you explain what model predictive control is in this paper? And let's see how that goes. Learning the latent world model. Oh, he explained it immediately. So let's see. Model predictive control. So at test time, use the learned world model to simulate possible future action sequences in latent space. Yes. Choose the action sequence that seems to reach the goal best. Execute it, then repeat. So it seems that it just does random trajectories on imagination space and picks the most promising ones. Kind of like an evolutionary approach in imagination space. I find that to be elegant. So the world model is not directly observation action, it's more current observation, candidate actions, predicted future latent states. Interesting. Okay. Model predictive control does not usually commit forever to the whole plan. It keeps replanning using the latest real observation, which helps correct model errors. Yes, that makes sense. Because you don't plan from... Ooh, okay. So you make the path in imagination space that you want to take. You take it. You take action 1 in that path. Then you replan with the new information that you have. And then you can keep doing that iteratively until you reach the goal. That's elegant. I actually really like that. I mean, other than the critique that I have that, okay, you don't do random paths and just pick the best random path. Like, that is a hack that we can do right now because the model is really small. But it calls out to me like that's like doing let's hop on a game of chess, you and me, and I'm going to when I imagine how can I beat you, instead of imagining like possible candidate actions that I think are already good, you know, the gut feeling that everyone gets when they play chess, or really good people like a grandmaster, right? They already know the moves. They're not searching randomly. They already have candidate moves. What they do then, and the expensive part, is to search on the candidate moves and rollouts into the future of those moves, if you get what I mean. I imagine if this paper has like a future work section, it's going to talk about that. And if it doesn't talk about that, then that's going to be really interesting. That's going to be really, really interesting. And maybe that's something that I could implement, and I could see if maybe I can get some generalization. Because what I have in mind then is if I can implement something like this. Personally, the tasks I like most, that the ones they showed here, is just push the. What if I can implement something like push A, push B, push C, you know, all the way up to the to Z, right? To Z. What if I then train it on push A to push Y, and then see if it generalizes on push Z, right? What if I then train it on push A to push Y, and then also train it to know what candidate moves are good, and it starts getting that gut feeling? Would I be able to get the results that this paper gets, right? Just that when I add more training into this 15 million parameter model, I can get them much faster for specific tasks. That's the big asterisk here. But I wouldn't have to craft a handcrafted reward function. It can just look at the previously rolled out paths that led it to the objective and learn from that, instead of having to learn from, say, like a policy that I make, or like a handcrafted reward function. That would be what I want to do here, and how I would extend this work. Okay, so this is the new plan. I'm going to implement the world model, and once I implement it, I will expand the range of tasks from push T to push A to Z, see if there's generalization, and then try to make it learn on candidate trajectory so that it develops that gut feeling that, say, evaluation engines have in chess or in Go, for example. That's what I have in mind. It's trained solely from unannotated trajectories. Okay, learning the latent world model. We need to stop theorizing and keep reading. But I don't know. I had to make that point. Train on push A to push Z. To push I don't know, push N. To push Y and see if it generalizes on push Z. Check if I can make it learn the evaluation engine such that it can already pick good trajectories instead of relying on random. Would I be able to get the results of this paper? Would I be able to get the results of this paper in way less rollouts? Let me move my thing. Rollouts of this paper in way less rollouts? By doing more training. But I'm not looking for like slightly less rollouts. I'm looking for like genuine 10x less rollouts off of just implementing that. I wonder how that would go. I really do. Batch size. Okay, so back to what I was doing. Offline data sets, we consider fully offline and reward-free setting. I mean, technically it's not reward-free. Like, technically a reward that is going on here is the prediction loss and the regularization term. The one thing that really unsettles me about this is the regularization and what's up with that. Because, and that's the whole thing that, you know, kind of rubs me the wrong way about JEPA. But I don't know if the solution is just to train it in more environments, is to maybe force it to come up with good representations by making it take actions and making it reach goals. Because if your representations are useless, then you won't be able to reach any goal, right? And if that hypothesis is true, then we can do without SIGREG. Can we do without SIGREG? If we force it to achieve goals, which would then force it, hopefully, to have good representations. The problem then is you wouldn't be able to do offline RL. Not RL, my bad. Just offline learning. If with this hypothesis. Because you can only really pursue goals online, right? How can we adapt this idea to offline learning? I'm just noting down all the questions that I have as I read this paper. But not necessarily about the paper, necessarily about like how can this idea be extended? How can it be maximized, right? We consider a fully offline and reward-free setting. The world model is trained solely from unannotated trajectories of observations and actions. Without access to reward signals or task specifications, this setup aligns with the JEPA line of work. It's trained solely from unannotated trajectories. Okay, yeah. So no annotations. Without access to reward signals or task specifications. This setup aligns with the JEPA line of work, which aims to learn generic task-agnostic world models from observational data. Our objective is not to optimize behavior for a specific task. Right. So what I'm saying is the goals don't necessarily make sense here. But then I'm falling into the same problem that I was talking about earlier, is that, oh, what if I train it on enough specificities and we can do without the SIGREG. If the whole point is learning solely from observations, then what good does having a goal do if we only care about the representations? Because you can't have goals offline. So the whole point that I've been like going in circles around is like, okay, what if I add like an online part to this? That's not the point. The point is the offline part. But maybe that is fine. Because the problem with online learning is that you need to handcraft rewards. Now it's getting what if instead of handcrafting rewards, the training objective is not the goal, it's just being able to predict the world? Which you wouldn't need to handcraft. This is getting freaky. We consider a fully offline and reward-free setting. The world model is trained solely from unannotated trajectories of observations and actions without access to reward signals. I mean, but you still have to make the data set. Wow, I don't know. This is like actually like trying to find the right philosophy for this is really hard because like the world model still, like after reading like their philosophy and how they train this, like it still doesn't fully sit right with me, because I know it doesn't scale arbitrarily to any task. The only reason you can brute force hundreds of paths into the future and grab k paths and get the candidates, it's because it's just a 15 million parameter model. What if I wanted to, I don't know, scale it to 100 million, right? Would then SIGREG fail? Would it not be able to regularize across that many parameters? Or would then, I don't know, something like I wouldn't be able to produce that many paths. Or I wouldn't be able to computationally brute force to the objective. See, this paper is asking me to apply online learning to it. That is what's going on here. Through RL. Well, I don't know if RL specifically. Well, yeah, RL. I would have to RL it, because wait, but that's kind of beautiful. Wait, if this thing can offline learn and online learn, right? Every time it online learns, I can just grab that and put it and append it to the data set of offline learn, of offline data, and have it learn off of offline data in a very similar way it learns to online data. The problem then is that offline, it wouldn't do the planning. It does do the planning online. And then it starts to look really similar to how a reasoning language model start to look like, which is very funny. The difference then is where in action space is going on. Like, where is action space? In my theory here, action space would be solely in representation space, and then in the theory of solely transformer models, and then it's in vocabulary space, and you wouldn't be able to make a VIT to do things like these because that would then be pixel space, and you run into the problem where pixel space is fucked up. Like, because it's just too much. There's just too much to represent. Man. But to learn representations that capture environment dynamics that can later be controlled or adapted to a diverse set of tasks. The training data consists of trajectories. Okay, hold on. It is trained solely from unannotated trajectories or observations and actions without access to reward signals or task specifications. This setup aligns with the JEPA line of work, which aims to learn generic task-agnostic world models from observational data. Our objective is not to optimize behavior for a specific task, but to learn representation that capture environment dynamics and can later be controlled or adapted to a diverse set of tasks, which is what I'm talking about with online. But I think online doesn't help solely to the specific task. I think it might help the architecture itself and the regularization itself. And I can do transferable learnings. But what then this paper would be providing is the greatest representation that you could ask for. Not representation, a foundation that you could ask for. Oh my god. The training data consists of trajectories of length t composed of raw pixel observations O1t. Composed of raw pixel observations O1t. This is a lot of images that you're gonna be needing to store for all these environments. And associated actions A1T. Trajectories are collected offline from behavior policies with no optimality requirements. Right, because offline you're simply learning to predict the world. You're not learning to plan, and you're not learning to essentially chase goals. You're just training those representation and that predictor to be able to know what's going on. I see. And then I imagine then if you did online, then that would conflict with the predictor and that would conflict with the encoder. Because if you're using online learning to be able to learn task specificities, then you might catastrophically unlearn a lot of the things that were learned and a lot of the representations that were learned when looking at the at just the general offline objective of simply being able to predict the world here. Gosh, I have so many freaking hypotheses here that I want to try. And associated actions A1T. Trajectories are collected offline from behavior policies with no optimality requirements. They may be pseudo-expert or exploratory as long as they sufficiently cover the environment dynamics. As long as they sufficiently... What? The training data consists of trajectories of length t composed of raw pixel observations O1t, O1 to t, yeah, and associated actions A1 to t. Trajectories are collected offline from behavior policies with no optimality requirements. The problem with this, right, is that how are you going to offline collect data that is valuable? Because imagine, in the task of push t, action space is low. Even if you do random trajectories, what's most likely going to happen is you're going to push t and you're going to change essentially your reward, or you're going to get closer to your goal, right? But if you had a massive action space, let's say if you had to do something like, I don't know, what's something with a lot of action space? That would be like a really good example for this. It's hard to come up with that task. If you have to code it, there we go. If you had to code a program, the action space there is massively larger than push T. Offline off of randomness just wouldn't cut it. Which I guess supports my theory that what if you use online to create better trajectories and better data set offline? What if online learning can be used to create the offline dataset? What if online learning not only learns how to act and say the evaluator, but it also learns how to predict the world, like offline learning. Are collected offline from behavior policies and okay, whatever. They may be pseudo-expert or exploratory as long as they sufficiently cover the environment dynamics. Yeah, that is what I was talking about. How can you sufficiently cover environment dynamics if action space is massive in an environment? And I guess that's what they mean by pseudo-expert. Then I guess my point boils down to you can use online RL, I don't know if RL, but online learning to create those pseudo-expert trajectories in the first place instead of being random exploratory. Additional implementation details, batch size resolution, and sub-trajectory construction are provided in App D. Model architecture. The world model is built upon two components, an encoder and a predictor. The encoder maps a given frame observation OT. We saw this into a compact low-dimensional latent representation ZT. The predictor models the environment dynamics in latent space by predicting the embedding of the next frame observation Z hat T plus 1. Z hat being the one that is predicted. ZT plus 1 being the one that is actually observed, like the representation of the actually observed OT plus 1, right? Given the latent embedding ZT and an action AT, encoder ZT equals encoder OT. Okay, I'm guessing this symbol here, theta, means that its encoder is parameterized, or however you say that. And the predictor Z hat T plus 1 equals. That's a question that I have. Why does enc use theta and why does pred use phi? I think theta means parameterized function, but then why wouldn't pred use use theta if it's also parameterized in much the same way? No, in the same way. They're both transformers. Both are parameterized functions. They use different Greek letters simply to indicate that the encoder and predictor have different sets of learnable parameters. Okay, so if they were to both use theta, then they would mean that would indicate that they use the same parameters. Parameterized by phi, parameterized by theta, essentially. Okay, we're learning to read. The encoder is implemented as a vision transformer VIT. Oh, cool. Unless otherwise specified, we use the tiny configuration, 5 million parameters. So if this is 12 million, 5 million parameters go to the transformer, to the VIT, and roughly 7 million parameters are going to the predictor. Okay. With a patch size of 14, 12 layers, 3 attention heads, and hidden dimensions of 192. Okay. The observation embedding ZT is constructed from the CLS token. What? The observation embedding ZT is constructed from the CLS token. What is the CLS token? Embedding of what? Okay, hold on. Jesus Christ. Unless otherwise specified, we use the tiny configuration, 5 million parameters, with a patch size of 14. 14, yes. (12 layers, 3 attention heads, and hidden dimensions of 192. The observation embedding ZT is constructed from the CLS token. I don't know my VITs. I know like patch size, but I don't know what the CLS token is. Okay, can you explain to me what the CLS token is and what does it mean for an observation embedding ZT to be constructed from the CLS token? I thought the output of the VIT was the representation already. What do you mean we have to construct that from the CLS token? The VIT output is a representation, but is usually not just one vector. A VIT outputs a sequence of token representations. Right, because it's a transformer, it outputs it auto-regressively. Oh. What do you mean global summary? What? Yes, the VIT is a representation, output is a representation, but it is usually not just one vector. Not just one vector, it's multiple vectors. A VIT outputs a sequence of token representations. Okay, yes. Each vector then being the representation of a token. Okay. Oh my god. And that's what gets fed directly into the other model, and it's already in embedding space. It doesn't even need to pass through an embedding layer. Okay. The CLS token is one special token in that sequence, often used as the global summary vector for the whole image. How is observation embedding ZT is constructed from the what? What a VT does to an image. Okay. I know it does it cuts it up into patches and then processes each one. Each one becomes a token / vector. Yes. Then VIT adds one extra learned token at the beginning. Learned token. CLS. So transformer processes 257. What is a CLS token? CLS stands for classification token. It originally comes from breast style transformers. It is a learned vector added to the token sequence. Is it fixed? It's not an image patch. It is like special summary slot. Oh, so you can just say whatever in CLS. Okay, interesting. So like more information. During self-attention, every token can attend to every other token, so the CLS token can gather information from all image patches. Sweet. After transformer layers, the final CLS token is treated as a compact representation of the whole image. Oh, wow. What the fuck? So it only passes a CLS token to the predictor. What is the VIT output? The final VIT layer outputs one vector per token. HCLS. H1 is true, okay. Each vector has dimension 1 and 82 in this paper's tiny VIT. So shape-wise, VIT output shape. Okay, great. Where HCLS representation of the CLS token. Okay, yes. Okay, so you do output the embeddings of every single token, including CLS token, and CLS token is essentially extra information, pretty much. Because it doesn't really correspond to any image patch. It's just like, just do whatever you want with this. Which lets the model have more. Okay, cool. It lets the model like represent arbitrary things that it wants to represent about the image in the CLS token. I guess the global summary is an interpretation of that. Representation of the CLS token. The patch tokens contain local / spatial information. The CLS token is a global summary. Great. What does observation embedding ZT is constructed from the CLS token mean? Wait, so the embedding is only constructed from the CLS token? Or is it constructed from the whole thing? It means they do not use the whole... Okay, yeah. Okay, I was right. They do not use the whole sequence of patch tokens as the observation state. They take only the final CLS token vector. Great, and that is a representation. That is odd. I find that to be really odd that you would waste all the other patch representations of the image, and you would only use the CLS token vector as the as essentially a representation that gets passed to the predictor in here. Interesting. I will have to look at that in the code once I actually get to that, and see what if I can tinker with that, if I have any thoughts regarding it. I don't have any thoughts regarding the fact that they only use the CLS. I do. The problem is that, okay, if you have a VIT and you give it all the image patches and you give it the CLS token for it to be able to kind of do a global summary of the image, what guarantee do you have that the CLS token is an accurate representation of the whole image? How do you know that the VIT doesn't also need the other representations of the image patches to represent the whole image? Like, how do you know it just stuffs everything into the CLS token? That is a really good question. I have a question. I kind of feel odd about the fact that it uses solely the CLS token to send to the predictor in LeWorldModel. The problem that I feel is that A, you're wasting computation. B, what is your guarantee that the CLS token is actually a good representation of the whole image and that the VIT actually stuffs the representation of the whole image into the CLS token? How do you know it doesn't also require the other patch embeddings for it to be an accurate representation? What if it also stuffs other representations into the patches that are important for this? The one concealment that I might have to this is that maybe this is trained away. In training to have accurate representations, since LeWorldModel is trained end-to-end, that could also indirectly train the VIT to output the CLS token to be an accurate representation, but I'm not sure here. I want you to tell me if my doubts are correct and founded, or if they are incorrect and actually CLS is guaranteed or is close to guaranteed to be a good representation of the image, and if this is an active area of study. Hopefully that was clear what I meant there. Essentially, the question that I have is, you have this rich representation that the VIT produces on every single embedding. Why would you only give it the CLS token? Your doubts are correct and founded. Okay, hold on. There is no mathematical guarantee that the CLS token automatically contains all important information from the image. The paper is making an architectural choice. Use the VIT CLS token as a compact global state. That choice is common, but it's not guaranteed to be optimal. Okay. The best defense of the choice is exactly what you guessed. Okay, because the LeWorldModel is trained end-to-end, the encoder is pressured to put whatever predictive information is needed into the CLS token, since the predictor only sees that token. Okay, good to know I have 2 feet on ground. Like, good to know I understand what this paper means. But that is an empirical training pressure argument, not a formal guarantee. Which is funny, because they bash the other approaches, saying that, oh, their losses and everything else, it wasn't mathematically guaranteed to be stable and to produce good representations. And in here we mathematically prove that our sig reg loss does. But then they just go ahead and do this of like, okay, let's only send the CLS token and practically assume that will be a good representation. Which is funny, because this whole thing hinges on the embedding producing, like the VIT embedding, not embedding, the VIT encoder producing good representations. So that becomes another question. What alternatives are there, and is there a mathematically optimal, or close to mathematically optimal? I don't think we should talk in mathematically optimal terms here. What alternatives are there to sending the CLS token as the image representation? And can we get something that is proven to work or be a good representation, in the sense that under the same definition that this paper uses for the word prove? Because I don't think you can mathematically prove in if like one architecture is optimal or if a representation is optimal. If you do that, that's like holy grail material. If you can mathematically prove whatever is going on here. Okay, I actually want to read more here. This is interesting. Is computation being wasted? Partly. A VIT processes all patch tokens after several self-attention layers. They keep only the final CLS token. So computation, in a way, is being wasted. It is not wasted if it's an accurate representation, is what he's trying to tell me, right? But the computation over patch tokens is not entirely wasted because the CLS token gets its information through attention to those patch tokens, exactly. During each self-attention layer, the CLS token can attend to patches. CLS information from all patches. This is assumed. Like this is, we suppose the CLS is going to have information from all patches and it's going to be coherent representation because of the way we're training this end to end. So the patch tokens are like intermediate evidence that helps build the final global representation. Yeah. So not wasted computation. Well, wasted computation in the end. But if you were to also send patch tokens to the predictor, then I imagine that could also cause instability, and that could also cause. That could be a bit dumb, because then how do you know if you're sending patch tokens to the predictor? Like in my hypotheses, right? How do you know? That's kind of closer to pixel space instead of doing stuff in representation space, which is the whole point. Like we want to get a compression, and while the embeddings, not the embeddings, well, yes, the patch embeddings plus the CLS token is already a good compression. I guess only the CLS token is better. I wonder like what the dimensionality on the CLS token is. What is the dimensionality on the CLS token / length of that vector? Vector / representation. I swear to God, if it's only like 196, yeah. You're compressing an entire image into a 192 dimensional vector. Yikes. Like, okay. If anything, it's impressive that works. Like, it's impressive you can compress an image to that tiny of a space, literally 192 numbers, and you can get the results that this paper got. Jesus Christ. Okay. Where were we? Is the CLS token guaranteed to represent the whole image? No. Precisely. There is no guarantee. The CLS token is just a learned vector inserted into the transformer sequence. It becomes useful only because the training objective gives it a reason to become useful. Precisely. But I feel like that's indirect. Then again, these are just my feelings. If we can practically prove something or practically disprove something, that will be way stronger. So training encourages the CLS token to contain class-relevant information. Yeah, encourages is the key word here. Like encourages doesn't really force it. In the world model, the predictor sees only ZT, which comes from CLS. Therefore, the loss encourages the CLS token to contain information useful for predicting future latent states. But useful for predicting future latent states is not the same as complete image representation. You need to have a good enough representation. My question is, how can we ensure that CLS is a good enough representation? Which is, I guess, what everything in JEPA hinges on. How can we produce a good enough representation, whether it be through CLS or whatever other methods we use? That's number one. And number two, 196 dimensional seems really low to me to represent images. But this is just my feelings. We need to hop into the code. Oh my. Therefore, the loss increases the CLS token to contain it. Yeah, you already read this. Could important information remain in patch tokens and be lost? Yes, this is a concern. The model might store global scene information in HCLS, object level spatial details in patch tokens, which is important, local texture or position information in patch tokens, fine-grained memory geometry in patch tokens. Yeah, which is really needed for a lot of tasks. Maybe not necessarily for push T. Well, even though push T it only got like 83% success rate, which is like not groundbreaking. If it were to get something like 98%, that would be holy, like that would be pretty crazy. then one could make the theory, oh, since it's missing a lot of this patch information, could it be that that CLS is not enough? If the downstream model only uses HCLS, then anything not compressed into HCLS is unavailable to the predictor. Yeah. So your concern is valid. This is especially relevant for world modeling because control often needs spatial object details. Where is the object? Where is the gripper? What is touching what, etc. Like, imagine you were to scale this. Imagine you were to actually make a world model and train it in a data center. HCLS is not enough. Because what if you then give it, what if it's playing a game? What if it's playing Pokemon Red, right? And in one part of the screen, there's like, I don't know, like an NPC that you need to talk to. What guarantee is there that HCLS is going to include that? And is going to like faithfully represent that, when it also needs to represent the rest of the scene? I'm willing to bet that it won't. I think the patch for that particular place of the image that contains the NPC would, or contains the like an object that might be really relevant to the model or the predictor, right? Or the planner, or whatever planning method we're using. But HCLS would only be for global scene information. What I'm essentially saying is, yes, you need global scene information, and HCLS might be really good for this, but for a lot of tasks, you need patch-specific information that HCLS might not necessarily capture. And for something really small like the LeWorldModel, this might be fine, and it might do really good in push T, and might do really good in the task that they tested it for. But if you want to scale this, and you want this to scale it to arbitrary tasks and have it be better and maybe produce a richer representation of the world, HCLS is not enough for this. Is my thought, right? Why might this still work? Because the model is trained end-to-end with the bottleneck, precisely. During training, the only representation that matters, the matters for the prediction loss is this, ZT being the representation of projection CLST. Okay, yeah, CT equals projection CLST. Wouldn't this be CT plus 1? Whatever. The predictor never sees a patch token, so if the encoder wants to minimize prediction loss, it has to make CLST contain the relevant predictive information. So if the encoder wants to minimize prediction loss, yes, it's encouraging that indirectly. The gradient path is roughly, okay, I get it. SIGREG does not guarantee semantic completeness. I know that, we already talked about it. It helps prevent collapse. The paper gives empirical evidence, not a guarantee. Yeah. Which is flimsy. See, it's funny, if we go up here, provable anti-collapse, but not provable, or not at least guaranteed or somewhat theoretically guaranteed that the representation is going to be as rich as we want it to be. I just find it funny that they say other methods are worse because of provable X, when the core thing in this is not guaranteed or provable. But whatever. Where were we? Okay, CLS token. Embedding into a new representation space using a one-layer MLP with batch norm. The observation embedding ZT is constructed from the CLS token embedding of the last layer. Yes. Followed by a projection step. I wonder what this projection step is. The projection step maps the CLS token. Oh, it tells me immediately. Thank you. The projection step maps the CLS token embedding into a new representation space using a one-layer MLP with batch norm. Okay. I wonder why that is needed. Maybe I could do an ablation where I don't do this. This step is necessary because the final... Oh, thank you. It tells me immediately. This step is necessary because the final VAT layer applies a layer norm, which prevents our anti-collapse objective from being optimized effectively. Okay. Okay. Yeah. So far so good. Necessary because the final VAT layer applies a layer norm, which prevents our anti-collapse objective from being optimized effectively. Right. Yeah. I wonder how the layer norm it makes the sigreg objective, the one that's here. They mention it. I think it's lower this objective here. Sigreg equals this lambda sigreg. I wonder how the layer norm would mess with that. Like I don't know. I don't know how that exactly, how this would mess with that. Which prevents our anti-collapse objective. Okay. The predictor is a transformer with this, these params. These specificities here don't really matter as long as you pick good enough parameters, like good enough layers, attention heads, and dropout and parameters and whatever. You'll be good. Actions are incorporated into the predictor through adaptive layer norm. Okay. I don't know what adaptive layer norm is. Applied at each layer. The adaptive layer norm parameters are... Okay. So this is a good moment to just screenshot this. Hold on. Can you explain to me what adaptive layer norm is, and how is it used here? Please explain simply. There we go. The A.ln parameters, oh my god, thank you. He goes immediately. Is a way to let someone extra conditioning information here. Yeah, because you need to let the predictor already has the CLS representation. It also needs the action. And the way you inject that is through layer norm, adaptive layer norm. In this paper, the predictor is a transformer that predicts future latent states. ZT plus action AT, yep. Instead of feeding the action as just another token, they use the action to change the normalization behavior inside each transformer layer. What the fuck? Okay. First, what normal layer norm does in a transformer, each layer. Okay, yeah. Given a hidden vector h, layer norm normalizes it. This is so, if I remember correctly, layer norm is so that gradients don't blow up when you're training the transformer. Then it applies learn, scale, and shifts parameters. Yes. Normally, YNB are fixed learn parameters. They are the same regardless of the current situation, the current action. What adaptive layer norm changes? In adaptive layer norm, the scale and shifts are not just fixed parameters. They are generated from some conditioning input. Yeah, which is the, if you were to do the push T task or you were to do the robotic arm task, then it's generated from, oh, move down, move left, move right, etc. Here, the conditioning input is the action AT. A.ln does something like Y of AT, B of AT, which are learned, I imagine, small equals small network AT. Then A.ln H AT. Okay, hold on. What is H? But it's just the second part of the layer norm. What the fuck? So you change normalization depending on the input that you want to give the model? Why would you do that instead of just giving it an action token or an action representation? What? Simple intuition. Normal transformer predictor, some dynamics processing of every action. What? Okay. Why would you do adaptive layer normalization to introduce information about the environment, like the action that is being taken, instead of just adding that action as an arbitrary token or a token representation? Are there benefits to adaptive layer normalization? Are there cons to adaptive layer normalization? I can't think of benefits, but I can think of cons right now. The con that I can think about is that this might make training unstable if you make the transformer predictor block big enough. In this paper, the transformer predictor block is roughly 7 million parameters. What if you were to scale that to something like 50 million or 100 million? Changing the layer normalization might make training unstable. But that is just my hypothesis. I want to know what you think. So let's get to the bottom of this. I don't know if I'll have time today to do the full implementation. Maybe I can get it started, but maybe tomorrow I'll stream and fully finish it if I can't get it done today. I didn't expect this paper to be this dense, is what I'm saying. Your hypothesis is reasonable, but I'd phrase it slightly differently. Yeah, when it tells you this, it's just telling you you're wrong. I love how GPT tries to be sycophantic, but it can't. ADA-LN can be destabilizing if implemented carelessly, but it is also widely used. Oh, I didn't know it was widely used. Precisely because it is a stable and effective way to condition large transformer blocks. Oh, it's stable. Especially when zero initialized or used with residual gates. Okay. So yes, there are real trade-offs. What are the two options? Suppose the predictor needs to know latent state and action. A simple way is to just add the action token. That is what I would have thought was my first instinct. Or for a history, exactly. Then the transformer learns through attention how action tokens affect latent tokens. Precisely. ADA-LN instead says, use the action to modulate the transformer layers themselves. Hidden equals layer norm hidden, scale shift action, yeah. So the action changes how the layer processes the latent representation. You're changing the scale and the shift. This is the scale being, I think it was beta and gamma, which would usually be fixed learned parameters. These are no longer fixed, but they are learned depending on the action. But this is effectively just two scalars. So let's say that you have an action, like a very simple action. Let's say you have your robotic arm and you want to move it right. I can see how two scalars is enough to represent that. But what if you have a more complex action? Would two scalars affecting layer normalization inside of this transformer block be able to represent more complex actions? The main benefit is that the action becomes a global conditioning signal. Yeah, since it affects all the layers through layer normalization. You're essentially forcing it to take into account the action, which is simple and robust. Yeah, benefit is stronger conditioning. I don't need to read this. Benefit, efficient and continuous actions. Continuous actions. In control task, actions are usually continuous vectors. Exactly. Oh, so something like an embedding or a representation of an action. Yeah, you couldn't really make that continuous. No, you could. But you wouldn't be able to apply something like a vocabulary to it, like a vocabulary of actions. Does not increase sequence length. Yep. Zero in association can make it cons. It can be less expressive than action tokens. Is this literally what I said? Is this, oh, what if you have to represent a complex action? How would you represent a complex action with just two scalars? If the conditioning information is complex, a simple ADA-LN vector may be a bottleneck. For simple low-dimensional actions, ADA-LN is fine. But if the conditioning were rich, like a language instruction, a map, many objects, a long action plan, then it wouldn't be so good. Well, that is what I said. That is my critique. Because the ADA-LN changes internal activations, it can make the learned dynamics harder to interpret. With action tokens, you can inspect attention, which latent tokens attended to which. Because ADA-LN changes internal activations, it can make learned dynamics. Okay, so you don't get observability. But I don't really mind about observability in the network. We're not Anthropic, and we're not doing mechanistic interpretability research. Bad modulation can destabilize training. Yeah, that's what I thought. But this concern is really not as big as action representation. It's just two scalars. How are you going to represent complex actions? It may be overkill for simple actions. If action dimension is tiny, then adding it by concatenation or as a token might work just as well, precisely, rather than having to condition every single layer to normalize differently. Besides, it doesn't sit fully right with me that you're changing a normalization step that is just to kind of fix training or fix inference such that the grains don't blow up. Why would you introduce information in a norm step? Temporal alignment can be tricky. Okay, whatever. So I get it. Interesting. Then that's another question. Can we introduce actions as tokens instead of ADA LN. Adaptive layer normalization. Okay. Let's keep going. Where are we? I always forget where I am. The ADA LN parameters are initialized to 0 to stabilize training and ensure that action conditioning impacts stabilized training. Come on. That action conditioning impacts the predictor training progressively. The predictor takes as input a history of n frame representations and predicts the next frame representation autoregressively with temporal causal masking to avoid looking at future embeddings. The predictor is also followed by a projector network with the same implementation as the one used for the encoder. All components of so the SIG regularization works. All components of our world model are learned jointly using the laws described in the following paragraph. And this is a training objective, and we got to the meats of this paper. Training objective, our objective is to learn latent representations useful for predicting the future, i.e. modeling the environment dynamics. LeWorldModel training objective is a sum of two terms, a prediction loss and a regularization loss. The prediction loss prediction, teacher forcing. What do I mean by teacher forcing? Computes the error between the predicted embedding of consecutive time steps. Okay. This is easy to interpret. Essentially what's going on here is you get this is mean squared error. The bars you see here and the exponents, you're essentially getting the squared difference of these two vectors. Why squared? Because the bigger the mismatch between any element, you can essentially signal gradient descent like, oh, this is worse than small mismatches, right? So something like a 0.1 mismatch would get turned into like 0.01, and it's like, okay, don't worry about it. And something like a 16 integer mismatch between these two vectors would just blow up to 256. It's like, you really have to pay attention to this. And that is how you can interpret mean squared error. And now these two, z hat is just a representation from the predictor. You give it zt, and you tell it predict what's going on, predict what's going to be the next representation when I pass the next observation through the encoder, and it predicts z hat plus 1, and you get the difference between the actual representation that is observed once you can actually make the observation at time t plus 1, right? This is pretty easy to interpret. And here they tell you precisely that z hat t plus 1 equals the predictor that is parameterized by the transformer of the predictor. You pass it the representation at t of the encoder block, and you pass it the attention, not attention, my bad, the action at t, right? Action is passed through adaptive layer norm. ZT is obtained through the encoder block. Okay. Something that I want to know what that triangle above the what does that triangle above the equal sign mean? Is this something basic I'm missing? The triangle, it means it's defined as. Okay. I'm straight up just missing lingo here. Okay, so this is pretty easy to interpret. Through the prediction loss, the encoder is incentivized to learn a predictable representation for the predictor. What a mouthful. Through the prediction loss, the encoder is incentivized to learn a predictable representation for the predictor. Okay. However, this loss alone leads to the representation collapse. Precisely. Why? Because if you tell it to, if you tell the predictor at, not the predictor, if you tell the encoder, wait, hold on. Let me gather my thoughts. You're minimizing the loss between the predicted output and the predicted representation and the representation at t plus 1. What if, hypothetically, your encoder blocks decided, let's cheat this loss and let's output 0 for every single possible observation. And your predictor also, you know, colluded and agreed with your encoder blocks and went ahead, okay, let's just output 0, and everything is just going to be 0, and everything is just going to be nonsense, that we never are going to output a representation that makes sense. How would the MSC loss react to that? It wouldn't, because the encoder in here, and because z hat t plus 1 would perfectly agree with zt plus 1, even though the representations themselves are absolute nonsense, right? So that's why you need the regularization term for the loss, which, I mean, as I see that, I think that is the biggest architectural problem in Chepa, is the representational collapse. And I think that a simple regularization term is not enough to you know, prevent this. But whatever, this paper says it's proven against collapse, so maybe we're gonna find out some interesting stuff later here in these paragraphs. So, however, this loss alone leads to the representation collapse, yielding a trivial solution in which the encoder maps all inputs to constant representation. Precisely what I was talking about. To prevent this behavior, we introduce an anti-collapse reg term that promotes feature diversity in the embedding space. Right. So if you give it an image of a dog and an image of a cat, and an image of a dinosaur and etc., you condition it such that representations across the inputs are diverse. Interesting. I think that's a bit of a hack, if you ask me. Specifically, we adopted, here we go, sketched isotropic Gaussian regularizer due to its simplicity, scalability, and stability. SIGREG encourages the latent embeddings to match an isotropic Gaussian target distribution. And I think this is the point of the paper, why just look up isotropic, what was it? I don't need to bring this up. To match isotropic Gaussian target distribution. Is this just a regular Gaussian? Also called a spherical or circular Gaussian. Okay, is a multivariable normal distribution where the variable variance across every dimension is equal. Oh, interesting. The variance across every dimension is equal. Let's look at images. Gosh, I can't look at that. I don't have enough zoom. I should get like a zoom utility in my computer here. Let me just keep reading the Google. And there are no correlations between dimensions. Oh. Okay, so if I'm getting this correctly, there's a constant variance across dimensions, and there can't be correlation across dimensions. You're preventing, how I interpret this is you're preventing the encoders from cheating. Like, you're pretty much just forcing it to output representations for different inputs that are not correlated dimensionality-wise, and that have constant variance dimensionality-wise. And the hope is that that forces it to output interesting or proper representations. Suddenly, I like this regularization term. I think it's good. I still think it's a bit of a hack, and I still think it's like, in a perfect world, we wouldn't need a regularizer, and it would just learn the representations. But maybe this guy's not so bad after all. Due to its simplicity, scalability, yeah, we read this. Okay, so we're gonna get into the math heavy side here. Let the Z contain in R and BD, where what is N? N is the history length. History, I imagine, being the trajectory. So if you take several actions in an environment for the offline data set, you call that the history N, batch size B, and D denotes the embedding dimension. Okay. So that's the Z. Assessing normality directly in high-dimensional spaces is challenging, as most classical normality tests are designed for univariable data. and do not scale reliably with dimensionality. Okay. SIGREG circumvents this limitation by projecting embeddings onto m random unit norm directions. Okay. And optimizing the univariate EPS-Pulley test statistic. They're losing me here. along the resulting one-dimensional projections, as illustrated by the Cramer-World theorem. Matching all one-dimensional marginals is equivalent to matching the full joint distribution. Okay, this is the point of the paper where I'll just take a screenshot. Can you explain this paragraph simply? You can get pretty crazy with this normalization terms. Okay, so let's see what's going on here. Prevents collapse by forcing the latent embeddings to look like a nice spread out Gaussian cloud instead of all becoming the same vector. Yeah, that is the variance between dimensions that we were, and no correlation between dimensions that we were seeing. So this is the collection of latent embeddings produced by the encoder. Yep. Each latent embedding is something like, okay, so you get all the embeddings across a batch. So when you're training, you train in batches. You get all the embeddings in the batch, and all the which obviously it has to be multiplied by n because the embeddings follow a history. Okay. History length, number of time steps precisely. Contains n times b latent vectors, each of dimension d. Example, history length n equals 3 batch size b d. Okay. This is just, what is SIGREG trying to do? Wants these latent vectors to look like samples from standard Gaussian. I understand that much. Why not directly test if z is a Gaussian? Because z is high dimensional. Okay, this is what they're talking about. Because z is high dimensional. If d equals, each embedding is a point in 192 dimensional space, testing whether a cloud of points is a Gaussian in 192 dimensions is hard and expensive. Yes, that is true. Most classical Gaussianity tests are designed for one-dimensional data. So you project it to one dimension. So the paper uses a trick. The trick, project high-dimensional vectors onto random lines. Why random lines? They choose m random directions. Okay. And these are unit vectors. Each direction is each direction is a unit vector in d-dimensional space. That just means, and they test along each direction. Then they project every embedding vector onto that direction. This turns each d-dimensional vector into a single number precisely, and then they test on every direction. So for one random direction, all embeddings become a bunch of scalars. Now they can use a simple one-dimensional normality test. And the hope is that over enough one-dimensional vectors, right? If you test Gaussianity over enough one-dimensional vectors, statistically this converges to testing Gaussianity for the whole high-dimensional space. And it is really hard for the encoder blocks to cheat this. Interesting. What is the EPS-Pulley test statistic? T is a statistical test that measures does this one-dimensional set of numbers look Gaussian. So T, H, okay. Gaussianity error for the projection along random direction M. If the projected values look like a standard normal sample, T is small. If they look non-Gaussian collapse weird, T is large. Then they average over many random directions. Okay, yeah. I get what's going on here roughly. Why does this work? Because of the Cramer-World theorem. Let's look that up real quick. Cramer-World theorem. It's a fundamental unit. Can I just look at the theorem, please? Let x v be divided with the mean vector invariance. I don't know enough math to interpret this. Just looking at the math, sadly. Is a fundamental result in probability and measure theory. It states that the probability distribution of a multidimensional random vector is uniquely determined by all its one-dimensional projections. The probability distribution of a multidimensional random vector, the high-dimensional point cloud, not point cloud, my bad. Would it be point cloud? Did that mention a point cloud? Dude, I'm so confused. No, it's just for the vector. Yeah, just several points in, which is I guess a point cloud, but it's not. Okay, let me just shut up. Probability distribution of a multidimensional random vector is uniquely determined by all of its one-dimensional projections. Yep. By all of its one-dimensional projections. Okay. So it's not that it's not just that it converges to it being a Gaussian. It's that it provably is a Gaussian if it's uniquely determined by all of its one-dimensional projections. But you wouldn't be able to get all the one-dimensional projections, right? You only get a finite set that approaches that. But it approaches it really fast. Right. Would the encoder model be able to cheat? Is the question here. Interesting. So a high-dimensional distribution is determined by all of its one-dimensional projections. In other words, if every possible projection of your data onto a line looks like a Gaussian projection, then the whole high-dimensional distribution is a Gaussian. And it makes sense why that works. You can imagine this in two dimensions. If I were to project it horizontally, if I have a Gaussian distribution in 2 dimensions, project it horizontally, then project it vertically, right? If you get Gaussian distributions in both axes, then it must certainly be a Gaussian distribution in the high-dimensional space. And you don't need to do the expensive Gaussianality test. Is it exactly that? Why this prevents collapse? If the encoder collapses, then projecting onto any direction gives nearly the same scalar precisely that does not look like Gaussian distribution. So sigrect gives a high penalty. To reduce sigrect, the encoder must produce good representations. Okay, great. So additional details on sigrect and definition of the Epps-Pulley statistical test, which I imagine. What is the Epps-Pulley statistical test? I just saw this guy hop on stream. Oh my god. You are lurking my stream. I'll hop on Slave Spire soon enough. Imagine your latent vectors. Okay, hold on. The Epps-Pulley test is a statistical test for checking whether a set of numbers looks like it came from a normal Gaussian distribution. Okay, and that's the Gaussianality test I use. Okay, perfect. I don't need to know the specifics of this. I think so far as I precisely understand what's going on here, I'm cool with not exactly knowing the specifics of the reg terms, interpreting the terms in here and stuff. But I think I now know. It's just projecting into several unit vectors and doing the Epps-Pulley test on that. So cool. And then that would be the loss. Pseudocode for the training procedure. Oh, and we're already in training. Pixel observations are encoded into latent embeddings, and a predictor estimates the dynamics by predicting the next step embedding condition on actions. Hold on, I'm actually reading, I'm not understanding. What am I saying? Pseudocode for the training procedure of LeWorldModel. Pixel observations are encoded into latent embeddings, and a predictor estimates the dynamics by predicting the next step embedding conditioned on actions. Yeah, you need to say condition because you're not giving the actions as tokens. The model is optimized end-to-end using a next embedding prediction loss together with a stepwise sig regularization term to prevent representation collapse. Def LeWorldModel, embedding encoder OBS. God bless PyTorch. Next embedding predictor, embedding actions. Even if it's pseudo-coded, like PyTorch, it looks really similar. FMSC loss, embedding SIGRAG loss, mean SIGRAG, embedding transpose. Yep. F dot MSC loss, embedding 1, next embedding, SIGRAG loss, mean, the average. Return pred loss, okay, awesome. The method introduces only 2 training hyperparameters, the number of random projections M used in SIGRAG and the regularization weight lambda. Yeah, that's what I thought. Because you can't, how many random projections are you gonna do, right? The whole point is that over enough random projections, depending on dimensionality. I wonder how, I need to check that. How does random projection EPS pulley test approach the full Gaussianality test on the dimensions, on the high dimensional space as you scale M being random projections. Latent planning, okay. The method introduces only 2 hyperparameters, yeah, M and projections, and lambda, which is the penalty. Like, you can interpret lambda as the weight of the SIGRAG objective of the loss. In practice, we observed that the number of projections has a negligible impact on downstream performance. Interesting. So I can't really cheat yet. Making lambda the only effective hyperparameter to tune. This greatly section 4. Oh, I'm gonna have to look at these sections. This matters greatly. Maybe some of these questions will be answered by that. This greatly simplifies hyperparameter selection, as lambda can be effectively optimized using a simple bisection search with logarithmic complexity. Okay, yeah, logarithmic complexity. And that explains the question I had earlier. What do you mean you're logarithmically able to tune hyperparameters? Because you can just do a binary search on lambda and figure out the correct weight for the SIGRAG objective in the loss, which is what they did in what I imagined was their ablation studies. And now they have really good lambda, and they don't feel the need to. Well, they don't feel the need. They just didn't find much meaning in tuning the projection hyperparameter, because I imagine for 196 dimensions, 1024 projections is way more than enough for testing if the distribution of the representation does follow a Gaussian distribution. Okay. This greatly simplifies hyperparameter selection, as lambda can be effectively optimized using a simple bisection search. Bisection search? Isn't this just binary search? Am I trolling? Is bisection search the same thing as a binary search? Yes, it's essentially the same idea. Okay, same idea. The slight difference is usage context. Oh, I don't care. Okay, it's the same thing. Great. Just that for finding a value, call it bisection search, and for what? I shouldn't have undone the thing. Please tell me the difference in context. I actually do care. Use a simple bisection search with logarithmic complexity. They don't need to state that binary search is logarithmic complexity. Bisection search is usually for finding a value root threshold in a continuous interval. Oh, and binary search is discrete. Okay. Yeah, but it is the same thing. Okay. So we do not employ stop gradient exponential moving average. This was all the hacks that the previous techniques employed to ensure that it followed. They weren't testing for Gaussian distribution. They were testing for that the representations were useful. They stop gradient and the exponential moving average techniques and etc. I really disagree with these. Gradients are propagated through all components of the loss, and all parameters are optimized jointly in an end-to-end manner, resulting in a streamlined and easy to implement training procedure. The training logic is summarized in algorithm 1. They're basically saying that the training objective here, thanks to their special regularization laws, is really good, and they don't need to do any of the hacks that the other techniques do. Now, I guess them saying that they don't have to optimize for the unit projections here to test for to test if the representations follow a Gaussian distribution, is them saying that essentially for 196 dimensions the model cannot cheat yet, or at least not cheat in a detectable way, such that the representations start becoming nonsense. But that is not proven. I don't think you can prove that. You can't really just look at a representation and prove if the representation is useful or not, as far as I know. What you can do is look at the latent space of the representations and argue that it makes sense by pointing at different representations and saying that, this cluster is self-similar, and you just analyze on a per cluster basis if you're willing to go ahead and make that argument, right? That said, latent planning, and this is the part that let it plan. At inference time, we perform trajectory optimization in our world model latent space, as illustrated in figure 4. Given an initial observation O1, we initialize the candidate action sequence randomly and iteratively roll out predicted latent states up to planning horizon H. The model predicts latent transitions according to z hat t plus 1 equals prediction. Yeah. Planning is performed by optimizing the action sequence to minimize a terminal latent goal matching objective. But this is task specific. They use MSC loss here. Oh, MSC loss on the representation space. Oh yeah, that makes sense. Okay, the only thing that is decided like task specifically is the representation of the goal. Awesome. This is easy to understand, where the hat horizon is the predicted latent set at the end of the rollout. The goal is the latent embedding of the goal observation OG. The world model parameters remain fixed during planning. This procedure corresponds to a finite horizon optimal control problem. Finite horizon optimal control problem. Okay. Which we solve using the cross entropy loss method, a sampling method that iteratively selects the best plan and updates the parameters at the sampling distribution with the statistics of the best plans. The planning horizon H trades off long-term look ahead against increased computational cost and model bias. In particular, autoregressive rollouts accumulate prediction errors as the horizon grows. Makes sense. Like, essentially, you're saying that if you make the horizon too big, eventually at step 500 something, it's just not going to make any sense because it accumulates errors. Like, if I imagine, I don't know, if you sit down and you imagine like a river flowing, maybe the first couple of seconds it makes sense, but at some point you will diverge and be wildly different from reality because there's just a ton of things that you can't predict, or maybe you're not, and you're not obviously optimally trained, right? In particular, autoregressive rollouts accumulate prediction errors as the horizon grows, which can deteriorate the quality of the optimized action sequence. To mitigate this effect, we adopt a model predictive control strategy. Only the first K-planned actions are executed before replanning from the updated observation. Yep, so you plan in steps, you plan up to a certain point, and then you redo the plan. And the whole point is that you can get those fine-grained, really accurate couple of steps after that are highly accurate, right? Before planning from the updated observation, we provide more details on the planning strategy in Appendix D. Environments used for evaluation left push T, we saw these. In push T, you have this little ball that the agent controls, and it just needs to push the T to the target destination. You have mechanical arm, you have two room, which is it has to move a red dot to here, and then you have, I don't know this one. Two joint arm needs to reach a target configuration in a 2D plane. Okay. So very simple stuff, which will be fine for 196 dimensions. Latent planning performance, planning evaluation setup, environments. We evaluate the LeWorld model on a diverse set of tasks, including navigation, motion planning, and manipulation in both 2- and 3-dimensional environments. All illustrating it. Well, there's only one 3-dimensional environment, man. Well, at least in here. Well, how many? I won't get ahead of myself. We provide more details on a dataset generation environment in App 3. I don't think this matters much because we're done really discussing like model architecture and all that. This is pretty much just implementation details for these tasks. Baselines, we compare the performance of the LeWorld model against several baselines. Yep. Among these baselines is the closest to our setup as it learns a world model end-to-end directly from pixel observations. So PLDM is literally the LeWorld model, but without representation space. However, it relies on a 7-term training objective derived from the VigReg criterion, which introduces training instability and increases the complexity of hyperparameter tuning. Dino is frozen and it's pre-trained from Dino v2 as feature encoder to mitigate representation collapse, but its original formulation additionally incorporates other modalities such as proprioceptive inputs for a fair comparison. Proprioceptive inputs. Oh, so you're giving it, oh, but that's cheating. You're essentially giving it proprioceptive in this case means, say you have a robotic arm, right? And you have OG bench cube, and you have to move the cube somewhere else. For the Dino example, you not only give it the image of the arm, you also give it proprioceptive inputs like the freaking coordinates of the arm and like the rotations of the joints, which is like why do we even bother with the image at that point? Just give it all the proprioceptive inputs and give it the input of the cube as well. And oh my god, and just have it. And don't even do Dino. Just do an FFN as feature encoder to mitigate representation collapse. But its original formulation additionally incorporates other modalities such as, for fair comparison, we exclude proprioceptive information from. Oh, but they do exclude from Dino World model. Yeah, because it wouldn't be a fair comparison if they gave it proprioceptive inputs. Additional implementation details for the baselines and evaluation settings are provided in the appendix. For each method, we keep the hyperparameters fixed across all environments. Okay. Towards efficient planning with world models, we report planning performance. The world model improves over PLDM, which also does planning latent diffusion model. I'm not sure what it could stand for. On the more challenging planning tasks, achieving an 18% higher success rate on push T, while remaining competitive with Dino World model, notably on push T, LeWorld model pixels only surpasses Dino World model, even when Dino World model has access to additional proprioceptive information, demonstrating LeWorld model's ability to capture underlying tasks with relevant quantities, moreover when wait, hold on. Higher success rate on push T while remaining competitive with Dino World model. Okay. Notably on push T, the world model pixels only surpasses Dino World model, even when Dino World model has access to additional proprioceptive information. Oh wow! Oh, this is crazy. So just from the image alone, the world model can surpass Dino when Dino literally is cheating because it has the integers of integer information. Scalar information of its environment. Well, not its environment as a whole, but of its, say, robotic arm. Come on, man. Demonstrating the world model's ability to capture underlying task-relevant quantities. Moreover, when comparing planning speedups... Oh, so this actually explains why Dino does so much better in OG Bench Cube, because it doesn't have to spend all this time with this complicated representation of a 3D scene. It just has the proprioceptive inputs, and that would explain why on something like push T, where proprioceptive inputs don't really matter much, what really matters in push T is, well, the position of the T block. Dino does way worse, 7x worse than LeWorld model. And why it's more closer on OG Bench Cube, because proprioceptive inputs here matter way more. And the world model, has to make complex representation of a 3D scene. Which makes sense. Okay. So it's not necessarily. So my theory that it was that cold pre-trained Dino already had like a good 3D representation. Like that's probably true, but I'm now leaning on it's probably more what I'm seeing here, that the proprioceptive inputs explain the difference in accuracy in these tasks. The world model achieves a 48 times faster planning time, with the full planning completing in under 1 second while preserving competitive performance across tasks. Yeah, because it's such a small model. This planning time is consistent across environments for a fixed planning setup, narrowing a gap with real-time control. We report planning performance in figure 6. The world model outperformed PLDM on a more challenging planning task, achieving an 18% higher success rate on push T, while remaining competitive with Dino World Model. Notably on push T, the world model Pixis only surpasses Dino World Model, even when Dino World Model has access to additional proprioceptive information. Demonstrating your world model's ability to capture underlying task relevant quantities. Interestingly, your world model performs worse on the simplest environment. On the simplest environment. Why would that be? Let's zoom in here. 2-room, which is simplest. Why does it suck for 2-room? I have a theory. I think it sucks for 2-room because of the funkiness that is going between the vision transformer, the 196 dimensionality thing, the 196 dimensionality compression into CLS token. I actually don't know, now that I think about it. This is interesting. It consistently, and it's much better in push T than 2-room, even though 2-room is like extremely easy. I don't know what's going on. That's another question. Why does it suck so much in 2-room? Despite 2-room being the simplest task. Come on, man. Reacher. I don't know Reacher. I know push T. I know G bench cube. What was Reacher? Oh, Reacher was the 2-joint arm. The world model, PLDM, Dino world model. But this is really nice that it achieves the highest score in push T. But I imagine the random rollouts is a lot of what helps it in push T. Because many of random actions, when you use cross entropy loss to zero in on the ones that are really good, end up effectively exploring the environment, even though it's just random. My God. Here it explains why it thinks the results are this way. Results are shown for 2-room, left researcher center, push T center, and OGBH cube. Okay, let's see. The world more consistently outperforms on OGBH cube. Yeah, higher visual complexity and the 3D nature of the environment. So it appears they have the same hypothesis that I had, why Dino World Model outperformed in the 3D environment. Which makes encoder training more challenging, precisely. I mean, you can't just train an encoder to predict 3D movement, like 3D dynamics, only on OG Bench Cube environment. That is not enough, but you could transfer learn that. In the simple 2-room environment, PLDM and Dino World Model outperform the world model, which may be explained by the sig-reg regularization encouraging a Gaussian distribution in a high-dimensional latent space, while the intrinsic dimensionality of the environment is much lower. Might be. And this is also a case against SIGREG or any fancy regularization terms. My. Two-room. A possible explanation is that the low diversity and low intrinsic dimensionality of this dataset make it difficult for the encoder to match the isotropic Gaussian prior enforced by, which may lead to less structured latent representation. This highlights a potential limitation of SIGREG regularization in very low complexity environments. Moreover, when comparing planning speedups, the world model achieves 48 planning fasting times, with full planning completing in under 1 second. But that's because of the amount of parameters in this model, no? Okay. Towards stable training of world models. What is integration not here? Yeah, bisection strategy, whereas PLDM requires search in polynomial time n squared. And to the 6. We also study the effects of the embedding dimensionality. Quickly saturates beyond a certain threshold. So this actually goes against what I was saying, that, oh, in 196 dimensions might not be enough for all scenes, but for these scenes, it appears that they're chill with 196 dimensions. Then again, you're also like supposing that it's going to fairly represent the whole image in the CLS token, which is not guaranteed. Like, there are fair representations of patches precisely in the patch tokens. So is a robust to the precise choice of encoder capacity. Additionally, we examine the impact of the encoder architecture by replacing the default VIT encoder with a ResNet 18 backbone. The world model achieves competitive performance with both architectures, indicating that, yes, of course it does. Because the whole point of the vision transformer are the patches, and ResNet, if you only... Okay, this is my theory. If you throw away the patches in a vision transformer, then why are you even using the vision transformer in the first place? The whole point and the whole richness in the representation of the vision transformer is the fact that the patches contain attention information. Whatever. The world model achieves competitive performance with both architectures, indicating that it is largely agnostic to the choice of vision encoder, precisely because you only chose to use one vector representation. Details on all oblations are available in AppJ. Training curves. We report the training loss curves on PhD for LeWorld model in Figure 18 and PLDM in Fig 19. The two-term objective LeWorld model achieves smooth and monotonic convergence. The prediction loss decreases steadily, while the sig term, regularization term, oh my god, I can't talk, drops sharply in the early phase of training before plateauing, indicating that the latent distribution quickly approaches the isotropic Gaussian target. Okay, contrast, PLDM 7 term objective displays noisy and non-monotonic. This is just I'm saying, okay, my training curve, loss curve looks nicer than yours. Come on. Okay, buddy. Yeah, we get it. Your loss curve is nice. SIGREM still doesn't seem like the answer to me for preventing representation collapse in JEPA. Maybe that is a bigger question here. Long term, what is the right way to prevent representational collapse in JEPA? Because SIGREG is not it. You can't use a purely mathematical regularization term to prevent representational collapse. It needs to be learned. That's what I imagine. Oh my god. Quantifying physical understanding in the world model. In this section, we evaluate the quality of the dynamics captured by the world model latent space either by learning to extract physical quantities from latent embeddings or by measuring the world model's ability to detect changes in physics. Yeah, they're testing that the latent is good. Physical structure of the latent space, probing physical quantities. Oh, right. Okay, so they're saying that the representation here, because they can use probes to get physical quantities, the representation here they're using that as a proof to say that the representation is really good. Oh my. I wonder. Let's just look at the graph here. Physical latent proven results on push T. Okay. Agent location, block angle. And this is a mean squared error loss. So this scales quadratically. Dino world model has 1.8, LeWorldModel has 0.05. I want to compare it to PLDM, because Dino world model is a joke because it literally gets proprioceptive inputs. So what is the point? So block location, okay, I don't know why they did this comparison here. They did block location on this task on, I imagine block location is for OG bench cube, where you have to get the, you have to move the robotic arm here. Why do you even put Dino world model here if it has proprioceptive inputs? Of course, the error here is literally nothing, because you can just add, like, you can just do like a linear transformation of the proprioceptive inputs, like where the robotic arm is, to deduce the location of the cube. You don't even have to look at the image. My God. I don't know if I'm a fan of these ablation studies. I guess the only interesting thing to look at here is the difference between PLDM and LeWorldModel. And LeWorldModel is roughly 2 to 3 times better here when measured under a mean squared error loss. So yes, I get it. You have really good representations for the encoders. Decoding latent space. To further assess the information captured in the latent representation, we report in figure 8 images produced by a decoder trained to reconstruct pixel observations from a single latent embedding. This is really interesting. This is one of the more interesting parts here. You can train a decoder to grab the representation and reconstruct the image, the source image that would produce that representation. Although reconstruction is never used during training, the decoder is able to recover the visual scene from the learned representation, confirming that the low-dimensional compact latent space retains sufficient information about the underlying physical state. Details on the decoder architecture are provided in AppD. That is really nice. I mean, 192 dimensions is nowhere near enough for something like OG bench cube. But I imagine that just straight up just decoding the latent space into an image is the quickest and best way to measure if the representation makes any sense at all, right? Then again, I wouldn't be too worried about regularization and preventing the JEPA model from cheating here, given the fact that the environments and tasks are relatively simple, and given the fact that we only have 15 million parameters to tune. Even the paper says it, like, oh, even making sig regularization stronger by modifying or altering the M hyperparameter, the projections for the Gaussian test across the representation space, didn't seem to do much, at least for this particular study, right? Visualizing latent space. We further visualize structure of the latent space using TSNE, provides a qualitative visualization of the latent space in the push T environment. The visualization suggests that the learned representation captures the spatial structure of the environment, preserving neighborhood relationships and relative positions in the latent space. Temporal latent path straightening. Yeah, this is just whatever. We're almost done with the paper, pretty much. There's just ablation studies and confirming. Look, I don't want to say it, but they're pretty much just saying that because they can recover the image and they can recover Like, what have we looked at? They've been saying that the loss graph of their method is nicer than the competitors. They've been saying that they have more observability and better interpretability of the latent space, and use that as an argument to say that the representation space makes sense through the probes, the physical probes here, and the decoding the latent space here. They're basically just empirically saying that their method creates better representations than other methods in the literature. Which, hey man, it's cool that you can empirically prove that, but I think I only really care about downstream task performance here. And if downstream, even if your representations are really good, if downstream task performance on the simplest task like 2-room, you are underperforming state of the art, that says something about your architecture. And that says something about, according to them, the regularization term that they picked, which in my opinion is the best in class so far, but it's still not it's still not as good as it can be. I really think that regularization in these models should be learned, and it shouldn't just be a math trick that is applied. It should be learned through it should be parameterized and learned through parameters, and it should also be directly addressed by the loss objective. But that is just my opinion that I will convert into see if it works once I answer these questions and I actually get into the coding of this. Which I think won't be today. I think I've done quite a bit by just reading this paper and understanding it. But I think tomorrow I will get into getting an implementation of this paper done and see if I can train it overnight. And then the day after that, I'll see if I can start testing some of the hypotheses and theories that I have regarding this architecture and how you're supposed to train this, right? Violation of expectation framework. They already talked about this. If they do something that physically doesn't make sense, is there an error, like a big error between the representation, the observed representation of the nonsense thing and the predicted representation? And they already talked about this. The answer is yes. So they can use this model to predict if something doesn't make sense physically. Predictor rollouts on push the OG bench cube. We visualize decoded latent plans. This is really cool. If you attach the decoder to decode from representation space here, you can actually see how the image gets blurrier and blurrier the more you roll out, which suggests instability if you stay on planning space too long, which makes sense. Like the more it imagines moving this robotic arm around, if you're on like step 500, you are going to get a blurry mess because errors are just going to compound on themselves. And it's not useful to plan 500 steps ahead anyway, which is why you pick a good enough horizon and you roll out until a certain point and then you replan from there. And now we visualize decoded latent plans produced by the LeWorldModel given a context and action sequence. Okay, yeah. Each rollout uses 3 image observations as context, which are encoded into latent representations, conditioned on the action sequence. The predictor auto-regressively generates future latent states in an open loop manner. All predicted latents are decoded into images using a decoder that was not used during training. Yeah, this is important because if the decoder is used during training, it's just going to cheat its way into knowing what the representations are. Well, that's number one. And number two, this sort of proves that the representations make sense, because if you never decode during training and then when you decode after training, you can get good decoding representations that basically tells you something that the representations make sense and that they're really good. At least for OG bench cube here. Effectively captures the overall scene, structure, and essential environment dynamics. Yeah, that basically you're saying the latent representation is good here. Some finer details, however, are not fully captured by the LeWorldModel. For instance, the angle of the end effector in OG bench cube. This makes sense because you're compressing the whole image, which might be, I don't know what, they never talked about the resolution of images they used here. But assume an HD image, you're compressing an HD image into a 196 dimensional vector. through a non-guaranteed method, which is the CLS token method they used here. I imagine if you were to also use the patches of the vision transformer and feed that into the predictor for it to create the next representation, not only A, would you get better predictions and better representations, you would be able to reconstruct finer details. It's not going to be precise because at the end of the day, you're still compressing information. You're compressing image into a representation and now you're decompressing, but it's going to be good enough. And autoencoders have gotten good enough to the point where you can kind of do that compression decompression loop that is lossy, but it's going to look really good in the end if you train correctly. Environments: 2-room, push T, OG bench cube. For each environment, we introduce 2 types of perturbation. They only have 4 environments here. They should have done way more environments. The first is a visual perturbation where the color of an object changes abruptly during the trajectory. The second is a physical perturbation where one or more objects are teleported to a random location, violating the expected physical continuity of the scene. The world model consistently assigns higher surprise frames. This is a very interesting way to say it has higher prediction loss, because of course it's going to have higher prediction loss if it does something that is aphysical, containing physical violations compared to their unperturbed counterparts. We provide more detail on the VOE in app. Okay, conclusion. This work introduced the LeWorldModel, a stable end-to-end method for learning latent world model environments based on JEPA to map image observations into latent space and predicted a model temporal dynamics in the embedding space by predicting future embeddings conditioned on actions. Great. Overall, the world model provides a scalable alternative to existing. It's not scalable yet. Scalable-ish compared to other alternatives. They need to fix the SIGREG problem, which I'll attempt to do and see like what we can get out of that. And they need to also fix the fact that you're compressing an image into only 196 dimensions. You need to include the patches. But if you can fix those 2 issues, the representational collapse issue, through like a more clever, maybe learned method, and you can also get a richer representation, this will be scalable and it will be really, really good. The stability and simplicity of training arise from explicitly encouraging latent embeddings to follow an isotropic Gaussian distribution to avoid collapse. Simplicity until it doesn't work, because it didn't work for 2-room, but okay. Outperforms approaches in data efficiency, planning time, training time, and stability while maintaining competitive final task performance. Yeah. Limitations of future work. Despite, I'm guessing that in limitations, they're literally just gonna they're gonna mention SIGREG. The SIGREG was the single biggest limitation here. Despite these promising results, several limitations highlight important research directions. First, planning with current latent world models remains restricted to short horizons. Hierarchical world modeling represents a promising direction to address long horizon tasks. They're basically saying, if I need to just push a T block to the correct location, doing planning in imagination, like millimetrically planning in imagination space is good and it makes sense here. But if I were to do something like, I don't know, want to plan a trip to Paris, I'm not going to millimetrically plan what happens every millisecond till I like, you know, do my trip to Paris, right? But that is a very, I guess, very crazy example. What if you didn't have to push T, which maybe takes a few seconds to do? You had to, I don't know, arrange something that could take a few minutes to do. Then these models would break down and they would have to, this wouldn't scale to that. Like this approach really wouldn't scale to that. And they're proposing hierarchical world models. I don't think you can build a hierarchical world model on the architecture in this paper until you fix SIGREG and until you fix the dimensionality representation. Here you can visualize the decoder cross-training, I think. So when you're training it, when 0 steps, you can see that it's complete random noise. 20K steps, you know, it starts to sort of make sense. 200K steps, you can see that the decoder can effectively decode from the representation something that makes sense, which sort of proves, that the representations are good, right? Same for push T, same for 2-room. Although 2-room converges much faster than push T, although these steps aren't really comparable with each other, which is annoying. Decoder visualization during training. They're just visualizing the latent space here. I don't really care about this. They've already shown that the latent space makes sense, and I believe them. And yes, I mean, they did outperform Soda on some tasks. Reasoning and planning. Second, our approach still relies on offline data sets with sufficient interaction coverage, which can be mostly or difficult to collect. In particular, limited data diversity can affect the effectiveness of SIG regularization in very simple environments with low intrinsic dimensionality, where matching the isotropic Gaussian prior in a high dimensional latent space becomes challenging. This is nonsense. You cannot measure the intrinsic dimensionality of an environment. You're just taking a wild guess. You're saying, I think that 2-room over here, since it's such a simple task, the dimensionality required to represent it is low, therefore it has low intrinsic dimensionality. While something like OG Bench Cube, the intrinsic dimensionality is way higher. But if you want the model that performs well in any amount of tasks, not just tasks that are low dimensional, also tasks that are high dimensional, and ideally much more higher dimensional than OG Bench, and much slightly lower dimensional than 2-room, because you can't really get much simpler than this. Then this architecture doesn't address that, and we shouldn't pretend like it does. We shouldn't say that it's like fully scalable up to that extent. Which, to be fair, they don't. But they do want to say that it's good. I'm not gonna let them do that. Where matching the isotropic Gaussian prior in high dimensional latent space becomes challenging. Pre-training on large and diverse natural video datasets could provide strong representation priors and reduce reliance on domain-specific data. I mentioned this. I am interested in pre-training on different environments. But this is just code. Like, it maybe it could fix the SIGREG problem, right? I think we should just blow SIGREG out of the water in the first place. Finally, current end-to-end latent world models depend on action labels to predict future states, which can also be costly to obtain. A promising direction is to learn future action representation through inverse dynamics modeling. Ooh, okay. So in here they're saying in the push T environment, where it's like push the T block to the correct location, you still need to label the correct location, and you still need to label like, what the goal is, right? Pushing T to the correct location and getting the label. Because I imagine you can get the label randomly, but how you're gonna get the right goal, correct? Inverse dynamics modeling, they literally just say, you have a physical system, any arbitrary physical system, you wanna get it to any arbitrary point, right? Inverse dynamics modeling is produce the correct dynamics, produce the correct set of actions that gets me to that point in the physical system, which in my opinion is close to how humans learn and is a really interesting research direction here. I agree with them that this is the way you scale this. The way you scale this is you just scale it to inverse dynamics modeling, because you can't just have someone hand annotate every single goal for every single environment that you want. You just get an environment, you have it imagine a possible state of that environment that it wants to get to, and it gets there, right? Violation of expectation evaluation across 3 environments. It just shows you that, yes, effectively, when something aphysical happens, it can't predict that, and it's surprised. It's a very liberal use of language. And we're done. Here's just references and the appendices. I'm probably going to look at this more when I actually sit down and implement this. I'm going to make a part here, implementation details. What is wrong with me? I should just use Markdown. Implementation details. Read the appendices in your off time. Because I don't think it will really be too interesting to stream, like me reading these appendices. Like, it's just details of how they chose to implement certain things, essentially. And baselines, this is just the other things they were comparing against. Okay, we're done. I think I'm done for today. I think I get essentially what is going on here with LeWorldModel. It's a very interesting research direction. I think it's way more interesting and way more correct doing building things on top of JEPA, where you plan and do computational representation space instead of doing it on pixel space. I think that is the big win over transformers, and I think that this paper is like a good first step. It's a good proof of concept that it can work and it can beat SOTA in certain tasks, specifically push T here. They shouldn't compare it to Dino, a world model. They should compare it to what's it called? To the other one, PDNL. What was it called? Oh my God. PLDM, right? Like, it's a good proof of concept, but it's not there yet. It's half-baked. It's half-baked because of the reasons I've been saying. SIGREG should not exist in maybe like a year. And things like just using the CLS token, like 196 dimension for representation, just shouldn't exist. How are you going to get patch-specific detailed data for an image? So very interesting. I think that I will be training this tomorrow. I think I'll stream again and just train this tomorrow and see if we can get a trained LeWorldModel doing different tasks like, oh, can it push a T, can it push an A, can it push a B into the correct location? And then we'll see if that generalizes into other letters, and I'll see if I can apply some techniques to this such that I can actually get better results than the ones in the paper, right? Because if I can do that, and if I can get results that beat SOTA here, then that's good enough to actually just turn it into a paper and have it be published. And that's why I wrote this little document here of the things that I question about the paper and the things that I think can be improved, and valid research directions that things can go in. But overall, this paper is really nice. If anyone chooses to read this in more detail, I would highly recommend it. Like, this is a really good paper. Thankfully, they do provide the code, and they do provide like a website for demonstrating like how this works. So for code, I'm gonna be taking a peek into it before I fully implement this myself. I don't want to do the slop implementation where I just tell ChatGPT, hey, look at this code, implement it for me, thank you. I genuinely want to implement it handcrafted because I need to push this further. And I don't think ChatGPT, I'm not gonna tell it, hey man, make a new SOTA, and it's gonna be able to make a new SOTA. So this kind of rests on me. But yeah, that's pretty much it. I think I'm gonna stop streaming now. Pretty happy with what was done here. I think it was like 3 hours of just digesting this paper. Only 12 pages, Jesus Christ. My throat is dry from talking for like 3 hours, but I'm excited. I'm excited to implement this and see where this takes us. So yeah, I hope you guys have a good one. Whoever is watching this, and I don't know if someone watches this in the future, good luck. And if you ever want to get into machine learning, just read papers and just implement them, because I think that's the easiest way to do that. That said, I'm gonna stop stream. Gonna wait a bit more. I'm probably gonna wait like a minute before I stop it, because my custom streaming software has this bug where if I stop streaming, it cuts out like the last 40 seconds. It doesn't, do stream until the last second. I need to fix that. If you're wondering, this is what I'm using. I haphazardly coded this like today, but it's pretty sweet. I just type like YouTube stream go into my terminal, and it starts streaming for me. So it's really nice. Now that said, it's been about 33 seconds, so almost there. Yeah. Thank you guys. Thank you if anyone watched. I don't know. I mean, I did see some people watch, but some of them were my friends. So yeah.